Oh, hello, hello. I'm trying to send something to everybody. Bear with for a second. And my computer is freezing. I'm assuming right now people can see me, and I'm assuming they can hear me. But even if you can't, just bear with for a second. If you don't, what is that thing called? The rainbow circle of mortality. The spinning disk thing on Apple computers is like, it's like not getting an exam score back when you're waiting for one kind of. Please stand by. Please stand by. You know, in these crazy times, okay, we might, believe me, when we get rolling, we're going to get rolling, but this thing might reboot, in which case I apologize in advance. Chat. Oh yeah. Oh, thank you. Thank you. I appreciate it, Ms. Isaac. Okay, we're almost there, I think. And the delay is I'm trying to send a document to everybody that actually, oh, thank you. Bravo. Okay. I do appreciate the patience. And what was I just about to? Oh, yes. I was in the waiting room. The whole waiting room thing is so dumb too. I understand that the waiting room doesn't even go on until I've gone on, in which case, what's the point really? But I do appreciate how patient you all are. I'm trying to send you something that I think you'll appreciate. It's a large file, and we will. Okay. Okay, I'm going to thank you for your patience again. If you are here, you've missed nothing. If you've been hearing the whole course, you've probably missed nothing, but you have done nothing. I'm trying to send everybody something in a moment. Here it comes. Yes, I believe I will possibly have to send another edition of this if this turns out to be wrong, but I'm about to send. Okay. All right. Some of you still, I'm going to start talking while this thing goes. A lot of you have now gotten exams back. Some of you still haven't. I cannot apologize enough. You certainly will have it. I'm just going. Trying to squeeze it in the cracks the same way you all are. You will have your exam back before you take your final exam. That is for definite. Like, that's for definite. And I apologize to those who still haven't gotten them back. They go faster and faster as they go. But a lot of you have, hopefully. And what, now I'm looking, okay. What I am going to do, this whole course, as you know, it's accelerated. We have 5 weeks to do all this material. I try to make it as chill as I can under those circumstances for my own heart rate. So hopefully it hasn't been as stressful as it can be. I think it is stressful if you haven't gotten a grade back yet. I know that. Why am I saying all this? Because what's still going to happen is you still have no new homework. You're still going to have a final exam that will be posted at the end of Wednesday, after of which you will have spent your lab period asking woo questions and reviewing material. He and I will go over that stuff tonight. What we're going to do. Oh, sorry. Yes. Sorry.
Sorry
Yes.
to cut you off, but everything you said before, like your voice cut out, so you just reconnected your voice. So we didn't hear anything.
Thank you. Okay, thank you. I'll start all over again. I'm actually relieved. I thought you were going to tell me that everything I just said was wrong, which would be harder to fix. But okay, I'll start all over again in 1 second. I won't try to do. Thank you for telling me that. And I might as well just not try to do 2 things at once. Hold on 1 second. This is, I think this pause of mine right now will be worth it to everybody if I can just do it. And then I will say everything I just said again, hold on, which was nothing. Here we go. I see. It doesn't want. Okay, I'll tell you all what file I'm trying to send right now, and it's a very large file. So okay, so I've started the upload now. It's going to take much. So remind me by the end of class to make sure that you have received in your Google Classroom email stream, whatever. What I'm trying to send everybody now is the full PDF, the full original draft or whatever of 3 old final exams fully solved. In other words, the full PDF of a book that I put on Amazon for this purpose to help people out, but it costs like $6 or whatever, and I haven't warned you about it sufficiently, and I'm not trying to make money off of you guys or anything off this, and I think at least one person already has spent that money, and I do feel bad about that, and I would like to actually reimburse that person or anybody else if they but what I want you to have is the contents of this thing. That is, there's 3 old final exams that are typical that I fully walk through and solve with explanations and stuff in this PDF that I'm now trying to send everybody. It's hundreds and hundreds of pages, of course, and I don't expect everybody to go through all this in one night or anything like that. What, in fact, I'm going to do tonight and tomorrow night is I will post like additional lectures instead of what you would call homework or whatever. I'll post a video of me walking through your midterm exam and where people lost points in general, like trying to explain why I took off points where I did or what to look out for. And I will walk through whether it's 1 lecture or 2, I'll walk through, one of these practice exams that's in this manual that I'm sending everybody. Of course, you'll have to watch those in order to get the full benefit. And that's where all the timing is tight no matter what we do. But what I really want to make clear to everybody is, and as bad as I feel about how long it's taking me to go through these midterm exams, like a sufficient number are now back, like a ton of them are back, where I can say like, there's nothing, I mean, obviously people used resources, and I told you you could and you should, but like whatever time you're going to spend on the resources, yes, you should go to other resources when I'm not clear, which is often for lots of people understand other people better than they understand me. Of course, that makes sense. But you want to at least know first what it is that I think I'm asking you or like going to put on the test and what I think I've said about it. You want to know, in effect, what's on the exam, right? Before you go like researching other things. And so the best way to do that is to research whatever materials I give you. Like one thing I do, just to make clear, like this extra lecture that I posted of the electric potential, the one that was a makeup lecture. So of course, I can see who has watched it and who hasn't. No, I can't. I don't mean that actually. And I don't want to know that. I mean, I can see numbers, as you know. I can see how many people have even turned it on. Now, I don't even really want to know that, frankly. It's like a weird invasive thing, but I do know how many people click on these lectures. And like, until everybody has at least clicked on the lecture, it doesn't make sense to go to Chegg or to go to other places and check things out. You should at least like let the lecture roll on some computer monitor somewhere in your house, in your apartment. Like don't pretend to be paying full attention to it. Don't try to fool me or yourself, but just let it roll so you at least see like what equations, I'm doing and then occasionally maybe tune in and see what I'm saying about them. Like I have lots of stories about that, but and it's not because I think I'm the best resource. I think I'm not, but I think I am the most direct resource to what I'm going to ask about on this exam. Now, the exam is going to be shorter than this midterm because this midterm is taking me too long to grade. It's too much of a bummer for everybody. The exam will be shorter, but it will be taken from those, like it will be a maximum of 1 question on circuits. And so I definitely suggest that you press woo as hard as you can for anything he has to say about circuits, which he has a lot to say. 1 on circuits, 1 on Gauss's law, which we're going to get right back to after I stop yammering, which we're going to get right back to today. So 1 on circuits, 1 on Gauss's law, 1 on magnetism, which I'm going to introduce today and finish today, and then 1 putting it all together. That's the maximum. I could chintz out and make the test shorter than that, and that's just that's good for everybody, but you do need to know those things to take the test. And again, you can take it fully open everything. But and I know I'm racing again here. A part of everything I'm yammering about is I think this is a really great class. As stressful as the situation is, I'm really enjoying this group. And so I do feel bad about dragging with your grades. But I also, I'm watching how my approach to online testing like compares to other faculty and other blah, blah, blah. And like, if you properly take advantage of this situation, there really is something to properly take advantage of. But if you misunderstand it, it is a misunderstanding. And what I mean by that is this: pretend physics is a French class or a piano class or something. Like, think of physics as a foreign language or a musical instrument. When I give you the guys a final exam, or just like when I gave you the midterm exam, in effect, I'm asking you to do a recital. Or I'm asking you, like, as though it were a French class, an advanced French class, I'm asking you, like, what are the causes of the French Revolution? You know, was Robespierre right in saying blah, 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 blah? Like, I'm asking you, in effect, an essay question in French. And I'm saying you can go all over the internet and like find out every expert in the world what they say about this classic essay question that I'm not pretending to have made up. And you can totally do that, right? You can go on the web and you can get all the experts in the world to totally weigh in on whatever I'm asking about the French Revolution. Again, this is an analogy. Oh, can you hear me now, by the way? Shoot, can you guys hear me now?
Yes, we can.
Okay, sorry. And it's okay, thank you. And by the way, I still haven't even repeated. The thing that you all didn't hear before, I don't think I have fully repeated yet. I will. But I'm trying to say, if you were to take a test in a French class where they asked, like, what's the causes of the revolution, whatever, you could find out the absolute best answer on the internet. But then your job is to come back and in your words, like, write an essay, right, about the French Revolution in French or whatever. So of course, what you could do is memorize an essay that you find on the web that you think does answer the question. You could do that, and I wouldn't stop you. But all of us who've ever been through school kind of know, like, that is so much harder. Like, actually memorizing a full essay in French, word for word, so that, because you know it's a good essay, memorizing it and writing it down is, for A, much harder than just reading the essay, understanding it, and then writing your own words about it if you're allowed. If you know French, right? If you know French, it is much hard, or whatever language we're talking about, Chinese or something. To memorize something word for word is what you do out of desperation if you don't really know the language. And the thing is, I just got to tell everybody, like, that comes through. If you try to memorize an essay about the French Revolution that you found online, and it was written in French or Chinese, like, if you actually just try to memorize or just like repeat phrases, it would come through that you don't speak the language. And I'm not saying that laughingly. Like, honestly, at this stage, many of us don't speak physics yet. Like, I actually do get that. But what you want to do is like view this as a language class, and to the best of your fluency of physics, show me that what you found on the internet actually makes sense to you in your mind, which really means, like, well, just that, like don't, like, find stuff that makes sense to you that you can break down and fits in your mind. You'll know, you know the difference between getting it and not getting it. Usually people in physics at this stage, if they're doing stuff, if they're like working hard, they'll stress about how they get what I'm saying sort of when I say it, or they get the answers to homework problems once they see them, but they're generally not confident about starting answers themselves, or they could see how the answer makes sense, but they still can't quite imagine how could they be that person coming up with that answer on their own. That is so fair. That is so fair. Like, I struggled with that like 10 years into my physics teaching. It's very fair to look at a physics solution and be like, whoa, yeah, that is right. Like, but whoa, I wouldn't have thought of that, even though every single step clearly makes sense, right? I struggle with that too, but that's the stage that you want to get to, where you appreciate that something is right. You appreciate how right it is and how it must be right. And you're like, I wonder if I could do that myself. Guess what? Here, I'm not asking you to come up with it yourself. I'm asking you to show that you get it, i.e. speak the language to me, okay? And a lot of you are totally doing that. This is not a criticism. I'm just trying to both say why these tests are more like essay tests and why they do take a little bit of time to grade in an honest way. And they take a little time to do in an honest way for you. What you want to do to me on the, what you want to do with me for me on the next final exam is really just think of it as I'm not looking for right answers. I'm looking to see that you can prove why the right answers are right. Like, it's all a big proof. You're proving that physics works, i.e. you're proving your actual understanding of the mechanism of physics. We all know the answers are out there. That's not the contest. The contest is to come back and show that you have fit the answers into your brain. Again, and by the way, I shouldn't even say many of you. I'm gonna say all of you. Like, any test I'm looking at, I can even see the difference in the test, whether you're strutting your stuff or you're like white knuckling it, okay? And I have I'm white knuckling it to teaching this class for sure. Like, I'm desperately hoping I get all your grades in, before everybody kills me. But then when I'm talking about Gauss's law, I'm not white knuckling it because I know it in my blood. That's what you want to show me on the test. Okay, blah, 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 blah. Which basically means, by the way, every time you think something is obvious, that's when you do write it down. That's the thing that scientists don't realize to a certain point in their science career. The stuff that you think is obvious is not the stuff that's not worth writing down. That's the stuff that is worth writing down, because the whole beauty of science is we break every surprise down into a bunch of little obvious steps. If you can convert the whole test, the exam, into like duh, like then that's a good thing. That's what you do with extra steps. Like, cross products take computations. They can't be done on one line. Even if you saw it that's something I keep seeing in this exam, the cross products, man. I believe that you could do it and check it, or look it up and check it and see it. But then if you only give me the skeleton of the steps, then it's up to me to just decide and assume that the cross product works in your brain. Please give me the steps, is what I'm saying. Anyway, okay. But people are still doing well. None of this means people are getting bad grades. Like, I still haven't seen a failing grade on the exam. I've not turned back one failing grade on the exam. So none of it means anything like that. But anyway, but please, like, tonight and tomorrow, like, in the effort to try to study, first of all, make sure I get you this PDF. Like, remind me by the end of this class, I'm trying to send you a PDF of 3 back final exams and full solutions. And just to use as a reference, to look up, you can look there how I would do a circuit problem. You don't have to read the whole thing or anything. But also, I should give you that by the end of this class. I will also post lectures of me going over the midterm and going like over a practice version of the final. Anything you find in those practice exams that I give you, this PDF, is fair game, but your exam will be much shorter. Like, again, please know the PDF I'll give you is 3 exams bundled together. I'll even be more specific as we go, but they're just there to show the material.
Will we be getting,
oh,
Professor?
Yeah, sorry, yeah.
Will we be getting, like we got last time, like you'll upload just one practice test, or are all the practice tests we're getting from this book?
Right, that's a very, very fair question, very fair. Assuming that this PDF does get to you by the end of this class, like assuming that someone can remind me and then confirm, yeah, we got it, then because I know it still makes it simpler just to have one thing, I will tell you all, like, of the 3 exams in that PDF, the one that I'm most working off, the one that I most recommend is blah. Like, I actually haven't decided that yet, but I will. So in other words, one of those 3 will be the one that I'm saying is like our Bible, so to speak. And that's what I'll post, I'll post a lecture about. So yeah, and then the other 2 will just be for practice or whatever. In the limited time, whatever you want for practice or for the future. Yes, I will select one as the most representative. And again, the solutions are in there. So when I put something online, it'll be trying to give you like hints and tricks and stuff. But yes, I'll once you get the PDF, I'll select one. That's a good point. What else? So again, sorry, yeah, go. I'm sorry. Yes.
Have you decided how long we'll have for the final?
Yeah, no, that's also a very, very fair question. Oh, wait, hold on. Okay, hold on. And I'm looking at all the. Oh, no, wait, okay. So I'm looking at sorry, these are all good questions, and I'm glad we obviously do need to talk about this. I just get nervous about time, but yeah, these are very good questions. So when I say these are good questions, I mean the ones that I just heard, but also I'm looking at private questions in the chat, so I'll try to address all these. Number 1, I actually wrote my department chair to absolutely make sure about when our grades are due. And unfortunately right now it seems like I said to her, our grades due Friday night. Of course I should know this, it's pathetic that I have to ask somebody, but and she has not said no. If that's really true that grades are due Friday night, which is kind of a disaster, then I have to stick with what I said, which is, yeah, then your exam will be due Thursday night at midnight. Like I need time to grade them before I turn in your grades. So as of now, your exam will be posted Wednesday night, and then you'll have to turn it in by Thursday midnight. As of now, I'll say that again. As of now, your exam will be posted after lab Wednesday, and then you'll have to return it midnight Thursday. I think that is tight. So I can say that the exam will be shorter than usual, or shorter than the midterm as a result of that. But if by tomorrow I find out that the grades are actually due later, I may extend that by a day for everybody's sanity. And if I do that, I won't change the exam or something. But yeah, as of now, you have 24 hours to do it from Wednesday, or more, a little bit more than 24 hours. And as of now, your lab period tomorrow should consist of practicing this with Woo, which means you'll all have the practice exam, including Woo, by then. So hopefully you would use the time really well, like you'd ask him questions that you already thought about, rather than just having just go over it, because the solutions will be there. But yeah, that's one question. That's a good question. Then another, I got a private chat. I know that in the case of a couple of exams, there are a couple of exams that I totally did get that I know Google says that I didn't get, but I did get, and those people haven't gotten their exam back yet, but it's not because there's an actual problem. Like, I'm answering at least one person's private chat. I know Google is telling you that you didn't. I have the exam, don't worry. I may be getting to it last because it's in a funny place according to Google, but it's not a reflection on the student or whoever's asking that. I promise that. Now about curves and stuff. Oh, wait, when's the last day to submit extra credit? That's also a fair question. The last day to submit anything, including old homeworks, okay? If I have not torn down a homework link yet, I mean, if you still see in Google that it'll accept an assignment from you, I will take any regular assignment and any extra credit. Certainly, certainly by Thursday midnight, let's say by Friday noon, okay? By Friday noon, I'll take anything, because certainly it'd be nice for you if you could do something like that after you weren't worried about an exam or whatever. So we'll say Friday noon for any loose ends like that. Again, if I learn that my grades are due later, then it sounds like I may be able to make this more flexible. Then someone asked, okay, now about curving. This a very, very fair question. Like, of course it is fair for people to worry about their grades and to worry about every aspect of them. Curving is a long, complicated thing that I sort of tried to explain at the beginning and explain in the syllabus, but here's but that doesn't mean it's not important. The thing with curving is your grades, for all intents and purposes, yes, do exist on a curve. Your final grades in the class. Like, the fast answer to somebody's private question is it possible to get a 75 on this exam and get an A in the class? Yes, it is. I mean, that is a very fair question. I'm not promising that you would. Like, I don't know the other details, right? But is it possible for someone to get a 75 on the midterm, especially now that I've seen most of the midterm grades, so like I know where the mean is and stuff. Is it possible to get a 75 on that midterm and get an A in the class? Yes, it is. I mean, is it guaranteed? No. Does it mean you have to fight on your final exam? Sure. But it assumes that you did really well in lab, and that you turned in a bunch of homeworks or will have by tomorrow. And if that's, and all things together, because of the way things are, I'll try to say this quickly, the way things are graded is you've got a midterm, a final, and you've got your lab average. Those three pieces get arithmetically meaned together. They get averaged. I don't as of this moment, I haven't curved the test exam grade, just for the moment, assume it is what it is. But I put those three grades together and average them, and then add to that a bunch of points that represents all the homework a person turned in. And some of that they might have turned in and still not gotten back. Like, just like some of you can still turn in homework late. Some of your homeworks, you know it. If it's in Google, believe me, you'll get credit for it. And the longer I wait, the more credit I have to give you, because I can't punish you for that. So it's, yes, it is possible to have received a 75 raw score on this midterm and get an A in the class. I don't curve the test grades. Sometimes I will say, okay, I'm gonna give an extra credit thing and I'm gonna add 4 points to everybody's test grade. Like, I might do that. If I do that, I'll tell you. I don't consider that a curve for complicated reasons, but assume right now your test grade is your test grade, but that is not your final grade. It's just not. Yeah, so that's a fair question. Oh no, oh, okay. And oh no, you guys are very kind. These are great. Let me see. I'm still trying to look at these chat questions. And I'm only, believe, again, I know these are, I'm only rushing because it's also just easier for me to talk about physics. Wait, oh yeah. Yeah, no, that's fair. Okay, hold on one second. Okay, I'll confirm again. And again, with these private questions, I totally get why they're private, but occasionally if they're private, that means people ask us. Anyway, the final will be released after lab on Wednesday. Like I'm assuming, and you correct me if I'm wrong, or it's just like anybody correct me if I'm wrong. I'm assuming that tomorrow you still have a scheduled lab period, your normal scheduled lab period, which for some of you is before and for some of you is after lecture. Is that okay? If that's true, okay, yes, okay, thank you. Okay, so assuming that's true, then I will release the final after you all get out of lab, or after half of you get out of lab tomorrow, so that you all get it at the same time. You'll have till Thursday midnight to do it. You will have opportunity, well, just that's the question, is so I'll release it tomorrow after lab, Wednesday after lab, and then you'll have till Thursday midnight to do it. Now, someone in the private chat just again fairly asked, can I please extend it to Friday? I totally think that's a legitimate plea. Like I want to extend it to Friday and I will try, but I can't extend it to Friday if the grades are actually due Friday. It's just, wait. All right, now I am seeing, okay. All right. So to reiterate again, yes, and I'm going all over the place. So I'm gonna try to stick with one question at a time. The last question was, could I possibly extend, the length of this exam till Friday night? I really, I would love to. That I can't do as of now, as of my understanding now, because the grades are due so fast. Again, believe me, the minute if I find out I'm wrong about the grades, I will change that because I don't want your exams that fast. Because as someone also asked, yes, there are still homeworks that I have to grade of yours. Now those aren't, I put them aside once we got into this exam, but they go a lot faster, of course. So yes, you can believe if you submitted homeworks and Google said you did, but you haven't gotten a grade, that is 100% because I haven't given you a grade on them yet. And the longer I wait, the more you can assume you're going to get nearly full credit on them. And no matter what, you're going to get a lot of credit. So I still owe people homeworks, yes. And and I need time to put those in. So that's why I'm saying right now, unfortunately, I can't have the exam go to Friday night. Now, someone else just proposed something very constructive in the private chat. Someone else just said, well, could we then release the exam earlier? That's a fair question. That is certainly a constructive solution. But for the moment, I unfortunately have to say no to that too, largely just because I'm not ready to do that. And also to tell you that's the main reason is I'm just not ready with the exam. Like the PDF, as you can see, it's taking forever, even for, I need you to have practice materials in your hand before I just release the hounds. And I don't want to over-explain this, but I just do want to stress, I think these are legitimate ideas. And whenever they can work, I'd like to make them work. But the reason I'm not going to just release the exam right now is there's a little bit of a tendency with these take-home open source exams. There's a little bit of a tendency with no bad intentions on people's part to start asking me a lot of questions once the exam has started. Like someone even just said that way. And of course that's fair because I could make a mistake somewhere in the exam. There could be an error. You want to make sure, Yaverbaum, did you really mean not to put a square root on this thing? Totally fair, right? But it's also dangerous because the one thing you're not really supposed to be doing is taking the exam with me. What I'm really trying to do is get you to have all your questions answered right before you take it and then pray that I didn't make an exam mistake. And here's the thing. I do make mistakes, but as it turned out in this last midterm, I actually weirdly didn't make any significant mistake. Like actually the questions are right, but more to the point, the PDF that I'm going to give everybody, one of the reasons I should have thought years ago to do this is the PDF is like from Amazon. Like I've edited it so many times. I think there aren't mistakes there. Like I had to make sure of that. So I think I can, and I'm going to make this exam a lot shorter and simpler. So even though I respect the idea of, can I just release it tonight? That I'm not ready to do. I'd rather have all you guys ask all your questions and freak out with me prior to it. But I will keep my finger on the pulse of like the grading deadlines. I'm the most believe me, in a heartbeat, I will extend how long you have to do the exam because I don't want it in my hands any more than you want a short period to do it. The closer we get, the more I feel like there's an emergency, the shorter I'm going to make the exam. That I will also tell you. okay, but I'm not prepared to start it earlier now, unfortunately. Also, it'll scare the crap out. I mean, we still have some material to get to today, so some of it would look really, really like annoying if you'd never even seen it at all. Okay, wait. I think these are most. No, that's a good question. It's return. Yeah, right. So okay, I think you can keep these questions coming, and definitely once I start the physics, definitely still if you have questions about the exam, keep them coming in the chat. I will try to stay on top of that. I will, I really will, believe me. My ideal is that I release this exam to you Wednesday night and then I find out I can give you more time. Believe me, that is my ideal. And if I did that, I might even make an office hours or something. I wish I could slow this whole thing down, especially because I think we're all getting into a groove here finally. But that's what I have to say about that. Yeah, the most blunt thing I can say is at this point in the semester, I've usually built up some intuitive feeling for something about the group or the individuals. If you ask me at gunpoint right now, is there anybody in that class that you think might fail? Like we need to know, we need to warn them. Is there someone who looks like they're failing or who's really got a problem? I would not have a person in mind to name, okay, based on anything I've seen. Like I hope no one's too panicked about this class because I think right now, hopefully we're panicking about the differences between maybe B's and A's or C's and B's, but but that should be the panic level. And that's big enough. Okay. I'm stalling slightly because I know. And thank you for the compliments that I'm getting in the chat too. They do. Yeah. Oh, wait a minute. Oh, wait a minute. Wait, that's really clever. Oh my God. Wait, all right. Sorry, I'm so dumb. Oh yeah, the story too. Okay. Wait, first of all, so from the same person who has private chatted a couple of constructive suggestions that I felt bad I had to reject, and I can see why these are private, because it's a risk to make such concrete constructive suggestions. So from the same person who one suggestion I just had to reject and I felt bad, there's one here that looks really, really usable. I need help with make a post. Right. I'm happy. What I will do, what someone's suggesting is, if I understand it, like I've never done this before, but I'm happy to make like how do you do that? You mean I'll post like a stream on Google Classroom about exam questions. I think that's what you mean. Like in the stream, I'll say, ask exam questions here. And that way, anybody who has any, like, especially if you think there's an error in the exam or something, anybody who wants to ask a question, as long as they're willing to go public, I don't even know if that's how it works, but as long as you're willing to put your question in a public stream, then I can watch the stream and answer. And right, I won't have to answer the same question 40 times and everybody can see. If that's what someone is suggesting here, then I definitely want to say yes. Yes. Okay, and thank you. If that's what you mean, that's a great idea. I never thought of it before because I'm an idiot or because some of this is new. That I will do. So because I'm assuming that means you guys can post into the stream of Google Classroom. I assume that thing is turned on. All right, we'll do that and please remind me. Also, please remind me that I need to get you this PDF. Is it even happening as we speak? Let's see. And those of you who already spent money on it, please tell me because I don't mean this. I mean, I see it. I mean it all as quiet integrity revenge on Chegg. Anything that it's not meant for you to give me money. So if you have, please let me know. But why? Wait a second. I'm just trying to get this. And I will start talking in a second. Also, the secret, one thing that is going to happen in this class, no matter what. Again, please understand, if everybody got an A in this class, I feel good, not bad. Like there's no law against that. I mean, I'll even say one time in my career, when I was at John Jay, but it was another department chair, like there was a time that I had a class where everybody did so well. The department chair did come to me and say, what happened here? Something's not right if everybody did this well, and I assume this won't continue. Like that can actually happen, as crazy as that sounds. But that's happened to me once in my life. And what I said was, I don't have a problem with it. And so nobody is ruled out from getting an A here, even in my fantasy life. But B, the thing is, I love this material so much. This whole physics 2-course thing is a story that has a punchline. And I am absolutely committed to getting to that punchline with this group. Like, even if I don't ask you the hardest question, even if don't get to ask you about it. I want you to see the punchline of all this material and before you leave and go back to the world of viruses. And that's what's going to happen. And no matter how hard or fast I have to go to get to that punchline, it doesn't mean you have to suffer. It just means you got to see it. All right, so wait, so I'm fixing this PDF. I think it'll work now. 1 second, and then I will start. Back. One more second. I'm gonna try with one more thing, and then if I have to give up for now on the PDF, just please remind me by the end. And I will tell you, and yes, somebody else in the chat said, because you've sat this long and waited, I will try to tell you the story quickly. There really are many. Oh, where'd it go? Come on, where is it? Oh, okay. Did that work? What? Ah. Oh, come on. Oh, is this what froze my computer? Are you guys, can you guys still hear me? This may be what's freezing my computer. Can you guys still hear me?
Yeah.
Okay, great. Okay. It is uploading now, this PDF. It's a lot. If nothing else has come across, I hope you understand anything that I've ever used as a resource to learn physics. And believe me, I have to learn, I wasn't born knowing it. Every resource I've used as a resource. Every textbook that to this day I like, or every manual that I now today like, is because I used it, not because I read it. I never read anything cover to cover any more than most of you. That's not what you do with these things. You look for what you need inside them is the point. And hopefully you're all about to get what I'm talking about. The thing that, yes, tell me. Okay, it's posting now. Even if this takes a while, it should be automatic from here on. I'll tell you a quick story. All right, so one summer, and again, I appreciate your patience. This is a story, then we're gonna get back into Gauss's law, which is much cooler than it looks. Because it would have to be, because it doesn't look cool at all. But the story is years ago, number of years ago at John Jay, I don't know, 2015 or something like that. Just like this, we had Physics 204 in the summer, but there was no virus. So we actually, met in a building and stuff like that and did stuff. But I still, that year, gave a take-home exam for the final exam for time consideration, so that we wouldn't miss the last 2 classes taking the exam. And even in that year, I said the same thing that I say now, which is, okay, everybody you got 2 days, go nuts, do whatever you want, talk with each other. I still believed then what I believe now, which is I think people should talk more, not less. And those of you who go to residential colleges, by the way, that is the one advantage that you do have over my dear, dear John Jay friends and family here. I love John Jay. I'm totally loyal to John Jay, and I think there's as much intelligence here as anywhere, blah, 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 and as much stupidity as anywhere. But the one disadvantage at John Jay is that people don't sleep in dorms, and therefore they can't just at any hour of the night be helping each other with this stuff. Those of you who can do that, like, take advantage. Please do. So this one year, I want to get the people talking as much as they could. So I said, you can all talk to each other, do whatever, but then you have to come in and report on this exam, like your own understanding, like, okay, just like I always say. So what happened that year was all of the students in the class, it was about this size, 45 or so, all of the students in the class actually got together. I don't know if totally physically, but I think they did. I think they all mostly got physically together, like, and a bunch of beer and stuff like that. And they had a whole session where all of them, almost all of them, knocked out the whole exam together, like, and, divided apart, and basically tried to totally nail the thing as a group, which I think a lot of them thought of as cheating. And I still was thinking of not as cheating and as almost a fantasy come true for me, if that's what was happening. The one thing was, it was like 7th grade where it wasn't all of them. It was like all of the cool kids. It was all of the students except a couple that they didn't invite, or they didn't get in touch with, or they didn't think would be useful because maybe those couple of students didn't speak a lot of English. Okay. One in particular spoke very broken English at the time, or sounded like he did anyway. Okay, so you can see where this is going, probably a lot of this story. Like, I graded all the exams. I knew, I had heard that they mostly got together. I didn't care. I just graded them as objectively as I could, whatever. And lo and behold, all the people that got together all group thunk themselves into a bunch of stuff that some of which wasn't really right. It was just what the whole group had decided. And they all put that stuff down. And the average score, and in fact, the most common score among that whole group was a 78. The one person who wasn't invited to the whole group got a 95. That person is Professor Wu now. I mean, he was a student then. He was told his English was not great at the time. Maybe it still sounds like it's not great. I don't know what it sounds like to you, but all I know is how he thinks in his second language is so much more advanced than how I think in my first language. I didn't know this about them at the time, but he rocked that course, and he rocked it by being the one person who wasn't invited to the groupthink. Now, what's the moral of that story? The moral of the story is first of all, invite Professor Wu to your parties. But the other moral of the story really is not that you shouldn't have a party and all get together and try to knock out an exam if you're allowed to. Like, absolutely you should. But you should do that, and then each of you individually should go home and see what you really think about the groupthink, and use the groupthink as data to enter into your own mind. Don't use groupthink as a conclusion. Like, you know, whether you want to make this into a political metaphor or not, like, the groupthink is data that you can't get otherwise. But then it's data. It's not your final understanding of anything. All right. Anyway, that's one story. Wait, do I have enough? So yeah. I don't think the other people cheated, but I think the other moral of the story is excellence just rises to the top. I love the fact that I was able to hire Professor Wu. I love working with him. And same thing with Walters. Like, they got hired because it's just clear they knew what they were doing. And you make that clear when you know what you're doing. Okay. But that's supposed to be a funny story, not a shameful story. If I do have time, I'll try to tell you one more story about me more on the cheating end of things, because I'm very sympathetic to how fast and hard all of this goes. But okay, any chance anybody's gotten this PDF? Does it seem like it's gone through? Can anybody confirm that in their email they got a PDF just now called Backfields SU19?
Yes, it went through.
Great. All right. So at worst, it may be intimidating and stuff, but definitely there's 3 exams in there solved, I think. And I will explicate which one is the best one. Well, maybe I'll even try right now. Wait, well, no, I can't do that right now. All right, I'm gonna try to go back to material now. Again, I apologize for all this. But I'll also say, you know, whether you go to John Jay or not, when all this is over, if you feel like you've gotten something out of this class, or you feel like you have been given an opportunity to show me that you do get some stuff, which I think a lot of you really have, you know, there are ways. It's not just about grades, right? It's also about recommendations and whatever your futures are and stuff. And whether you go to John Jay or not, I'm happy to, you know, stay involved and helpful with anybody who wants to stay involved and helpful in physics, or whether it's here or somewhere else. Okay, I guess that's my way of returning the compliment that I'm getting in the chat, but I mean it. All right. Okay. All right. I think we're ready. I think I've stalled out. So we go to 3. I'm going to start talking about electrostatic flux again. Let me just, I've lost entire. I'm just trying to get okay. We're back there. Oh, the chat. Oh, maybe I missed a lot of chat that time. I'm just looking to. Oh, cool. Oh, well, these are very. Oh my God. Oh wow. Oh, okay. Now I'm blushing. All right. I really appreciate everything that everybody said in the chat. That is and it's particularly because I really do know, I feel like you're getting short shrift by I cannot focus in my home. I don't know if that's clear at all, but if you're getting anything out of this, then you are a very flexible person, whoever you are, all of you. And it's too bad we don't get to talk about this virus, because it is crazy town. And I don't know who you all talk about it with, but it is crazy, this virus. Like, you all know that all the grown-ups in the world are totally faking this shit. Nobody knows what's going on at all with this virus. And okay, but now I'm only stalling because I'm getting the screen I'm getting the screen up. Okay. 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 Okay, this is where we were yesterday. Oh, and yeah, this came up in the exam. Oh, okay, quick point here. In the exam, okay, minor point, but just so you see what that gravity problem in the midterm exam, which people rocked on for the most part, but a common thing was to lose 2 points when I asked you, there's the gravity problem had 3 parts, A, B, and C. Each one it said was worth 10 points of the total 30. In A, you're supposed to like prove that you're supposed to derive F as a function of R and secretly kind of, that was the part where you're going to show formally why this thing is a harmonic oscillator and why we can use that information to get a number, right? So all of part A, there's no number. You're trying to prove something about F as a function of R. It is a proof. You do want to include as many steps as possible. You're not just trying to justify, you're trying to justify why we all believe something. Well, a lot of people lost 2 points because a lot of people they solved for the mass of the inner sphere, and then plug that into GMM over R squared, which is correct to plug in the mass of the inner sphere into GMM over R squared. But it's correct because what we're saying, because that's like the biggest insight and biggest move of the whole proof, which is to say, hey, if we're inside a solid sphere, we are stuck between an inner sphere and an outer shell. And we've already said that outer shells all contribute 0 to the net gravitational force. So all we'll have to do is worry about the inner part. And then that's why you solve for that and sub in, right? But that has to be explained. Like that is a thing. There's no reason just offhand just to ignore half of the sphere or to just arbitrarily solve for some inner part, right? At the time when you take the exam, you're supposed to say something, even just make a reference to the outer shell doesn't count because it all contributes net force of 0. Even that, I would say, honestly, if you really want to understand what's going on, you should be able to justify that statement. But you have to at least make that statement. There has to be an acknowledgement of that outer shell. So that was like 2 points for a lot of people, just to explain. It's not a big deal, but what we just found in electrostatics yesterday was a similar result. What we're finding now, but we're in a way we're generalizing big time and calling it Gauss's law. We're finding out that only the stuff inside matters. Like that's what we're saying in a different way now. We're getting that same field is directly proportional to displacement. We're getting this thing that I circled right here, E equals plus or minus. We ended up getting that the electrostatic field inside a solid sphere of charge is just like the gravitational field inside a sphere of mass, right? We found it out a different way using Gauss's law, but we're finding out a similar thing. I'm going to plow on, and Gauss's law is more powerful because it can find many things. The way we found that gravitational result just stopped there. There wasn't anything more we could do with it. Here, I'm going to go on and say, okay, technically what we found yesterday was the electrostatic field due to a sphere of charge, like a ball of charge, a solid ball of charge, plum pudding, charge everywhere. We found out what the field is at any point R outside that ball, and we found out anywhere inside that ball. That's what we have found out so far. Okay, somebody asked me this yesterday. I think I hate to, like, just to be super clear because I'm about to move on. What technically we've done so far, you could say, is case 1A. By 1, I mean it was a sphere. By A, I mean it was solid. It was insulating material. But even of 1A, we did 2 subcases, R greater than capital R and lowercase r less than capital R. That's what we've done so far. What I'm going to do now is move to 1B, the conducting sphere. Okay. And things, whoa, sorry, yikes. Oh my God, I just totally lost everything in the world. Oh my God, I seriously just broke the world. I'm sorry. Okay, okay. 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 We're now going to do case 1B, inside and outside. Why does it keep happening? We're going to do case 1B. Okay, this is now case 1B, the conducting sphere. That means we have a sphere. Oh, and I should say, I'm sorry, the stable conducting sphere. Okay, so just like yesterday, we walk into the lab, there's a ball in the lab like that has extra protons on it. Like somebody intentionally removed a bunch of electrons, like they took a glass rod and they like charged it up with like a cat fur or something, you know, like did some static electricity thing. And they, yes, we will do every case that I make you responsible for, we're going to do together like today. Yes, there aren't that many, but yes. So you walk in, there's this sphere that someone has intentionally charged it up, like they've removed a bunch of electrons, so it's positively charged, okay? But now the sphere is made of metal this time. And, you know, that means the charge can move around on it. It doesn't mean that the charge moves off it. Again, I have to often clarify this for people. Something can be charged or uncharged, and something can also be conducting or non-conducting. Those categories are independent of one another. This metal is containing all of the charge that we put on it until we attach more metal to this thing, and like until we attach a wire to it and put the other end of the wire into the ground of Earth or into somewhere, like this charge has nowhere to go. So we walk in and we sit and we see this net charged ball, but it is now made of metal. So now, oh, and the question again is going to be, what's the E field at points outside the ball? What's the E field inside the ball? All right, well, I guess let's get to it. What is E? This is always the question in this material. It's always given some situation, find the E field. And whenever we say find the E field, we really mean find the function. We mean how does the E field depend on space, on R. Like we're never looking for numbers. We're always looking for a function. So what is E as a function of R? And let's start by assuming that R is greater than R. So we'll assume we'll go outside, okay? Well, this is a Gauss's law question. So I'm going to do the Gauss's law procedure that I did yesterday. Step 1, draw the field line diagram of the situation. Draw the field line diagram. Okay, now we've just got a ball here, just like yesterday. So it shouldn't be that it's not going to be that crazy or intricate. It's just going to be super important to draw the free body diagram, just like the free body diagram of the pendulum. Just has like a couple of arrows, but where those arrows are make a big difference. But in order to draw the field line diagram, we need to know where, well, let me put it this way. We need to know how, sorry. Okay, so I'm using Gauss's law to figure out what the electrostatic field is due to some ball of charge. And the procedure according to Gauss's law is first draw the field line diagram. That's what we did yesterday with our ball of charge. Only yesterday I just drew it. I said, oh, okay, we got this ball of charge and the charge is everywhere like plum pudding. So now let's draw the field line diagram. I'm about to draw the field line diagram here, but this time I'm going to stop and say, but wait a second, where is the charge in order for me to draw the field lines? The reason I didn't have to ask myself that yesterday is because I was told in the problem, all the charge is everywhere throughout the body of the sphere. And I was told it was an insulator. So that meant wherever the charge was placed, it would stick there and stay there. And I could rely on that. Here, I don't know where people place the charge, but I know that we've got conducting material where charge is allowed to move around, okay? And I've been told that not only is this a conductor, but it's a stable conductor. That means I walked in, like someone placed the charge on this ball at some point, but then let time go past, like let craziness occur if craziness was going to occur. And until the craziness, whatever it might be, settled down, like they didn't let me in the room. Eventually I was let in the room and I walk to this and I see this stable ball of metal. The question is, can I can I use all that knowledge to be able to confidently picture where all the charge will be here, since it is free to move around? And the answer is yes. Okay, this is an English point. This is a heavy English point. Like it's not a math point, it's an English point. And if you miss it, then you miss a lot. But once you hear it, I think it'll make total sense to you. What I'm saying is charge in a conducting body, charges, electrons are free to move just according to the laws of physics. That is, they won't move at all, or they won't accelerate at all if there's no forces acting on them. But if there's a force acting on some electron, it'll accelerate according to that force until it lands in the next force and accelerate according to that. Well, in our terminology, what that means is that if electrons are in an electric field, or if protons are in an electric field, the field will accelerate them. It doesn't mean they'll travel along field lines. It means at any given one moment, wherever the field lines are, say, whatever the field lines are doing, will cause them to accelerate at that moment, like, so the field lines might be pointing to the right and a charge will then accelerate to the right. Now, I don't know how it was already velocitizing or not. It might be velocitizing up while it accelerates to the right. So it might start going in a curve or something, who knows? But then it's on another field line, so it will do what that field line tells it to do. In other words, charges don't necessarily move along one given field line. They don't. That is not a correct way to read field lines. But field lines do mean that charges accelerate. Charges will accelerate from one field line to another. So as long as there's field, there's charges accelerating, right? And there's so many charges in this ball. I have no idea what any individual charge is going to do at any individual moment. But as long as there's field through the body of this material, charges will be in motion. So picture, it's like what it becomes is a very interesting statistical phenomenon. You have a whole bunch of charges that are all basically, even if you don't like anything I'm saying about fields, if you just picture that electrons repel one another, which they do. So you picture a whole bunch of electrons crowded into this ball. We might have crowded them into the ball. We might have crowded them everywhere in the ball, but they're now jammed together. They're in a field due to one another. One electron over here is going to move away from so electron Ed is going to move away from electron Bill, right? Because they repel each other. But as electron Ed is moving away from electron Bill, of course, it might just accidentally careen closer to electron Mary, right? So now electron Mary and electron Bill are repulsed. So now they bounce away from each other. In other words, every electron wants to be far away from others, but as it gets farther away, it gets closer to others. So the electrons just keep scrambling and scrambling. Like, what keeps happening is different random configurations of, once you have a conductor, you allow for random statistical shifts in the crowd of electrons that are there. It's all the electrons will shuffle as though you're shuffling the cards in a deck. And that will go on for many, many, many iterations. And every possible way you could picture all the electrons being in a metal ball occurs at some point. Like, electron number one could be over here, or electron could be over there, and every possible arrangement you can imagine is as likely to occur as any other arrangement. But here's the big key. Just like when you shuffle the deck, any possible arrangement of cards is as likely as any others. But imagine we made up a rule in shuffling decks that if you ever happened to shuffle the deck and get all reds together and all blacks together, if we made a rule that said once you ever happen to land on that, you would stop shuffling, like, well, that wouldn't make it any more likely that you'd get all half red, all the reds together in half of the deck and all the blacks together in the other half. Like, just because you want that to happen doesn't make it any more likely. But if you make a rule that says when it happens, I'll stop, then eventually you'll stop shuffling, because eventually you'd hit that arrangement, just because eventually you'll hit every arrangement. That's what happens with electrons. In a conductor, charges fly around into every configuration. They scramble, they scramble, they shuffle, they shuffle, they shuffle randomly. And every possible arrangement is just as likely as any other. So you actually can't predict where they'll be, except for one thing. If all the charges happen to land in an arrangement that cancels out the field, if an arrangement is possible for canceling out the field and the electrons happen to fall into that arrangement, then if the field is all canceled, then the acceleration stops. Like, once the forces are gone, there's no more acceleration. So then the shuffling stops and it sits there. In other words, that's a long way, but it's a very powerful scientific, important principle. And it applies to natural selection in the biology kingdoms as well. What I'm saying here is, if you put a bunch of extra charges on a conducting piece of material and walk away, if you give it enough time before you walk back, then once you walk back, you will necessarily find all the charges as far apart from one another as they could possibly be without being any closer to any others. In other words, they'll maximize the distance among all themselves by equalizing it, right? Just like the maximum area that you can get for a given perimeter of four sides, like the maximum area you can get given a rectangle of a certain perimeter is a square. I said that really badly, but, or just like when you're shooting a projectile, right? If you want to shoot a projectile as far as possible, you might think, oh, I'm going to shoot it really like this so that the thing goes really far and doesn't waste any of its time going up, right? But if you go like this, then it doesn't get any height and the projectile doesn't get any time to go anywhere. If you shoot like this, it goes really high, but it doesn't go over anywhere. And the ideal way to compromise those two things is to shoot right in the middle at 45 degrees, and that maximizes the range of a projectile. It's an analogy. But what I'm saying is it's the same Maxman principle that applies here. The electrons will be as maximally far apart from one another as they can if they're uniformly far apart from one another on a surface of a body. There's no law in nature that says electrons must go there. But there is a law that says that if electrons happen to land there, if all the electrons happen to be uniformly distributed throughout the surface of some piece of material, then that will mean the field is zero throughout the body of the surface, and therefore the electrons will stop moving. So if you give electrons enough time, if you give net charges enough time in a conducting material, they will all be, this is the point. It's a long thing for me to say, but we need it. If you give a metal a long enough time, all the electrons will be uniformly distributed throughout the surface of that metal. And therefore, you'll see in a second, therefore the field will be zero throughout the metal. Like a stable metal has, yeah, let me put it as clear as possible. Here's really what I'm saying. And this is a surprise. This is exactly what people that don't do physics don't think. Honestly, this is why it's safe to be in a car in a lightning storm. And the answer, the reason is not rubber tires. I'm saying throughout the body, like the actual the body of a stable conductor, if you put a piece of metal down for long enough, you will not find any net charges throughout the body of that metal. In other words, throughout the body of that metal, you'll see in a minute, you won't find any electric field at all, i.e. it's safe. You won't be shocked inside the metal. And this has nothing to do with tires or anything else. It's that electrons will distribute themselves uniformly to the outside of a metal. So like a car, right? If you're inside a car and lightning hits the car, it spreads itself throughout the body, the metal body of the car. I mean, through the surface of the car, it'll spread itself out. Not right away, like, so, you know, I'm not exactly, I mean, the first millisecond might be dangerous, but it will do that. And it will stop by definition the moment it lands in that arrangement, because that arrangement is the zero field arrangement. So it's not that charges seek to cancel out a field. It's that they move and move and move until they accidentally cancel out a field, and that stops their motion. And guess what? This whole process of achieving stability takes a huge number of iterations for electrons to undergo, but it takes like milliseconds in our human time. So to make a conducting body stable, it just takes a couple milliseconds. So it's not unrealistic at all. And I'm saying now with all of this, thus, back to step one, draw field lines from conducting sphere. Okay, so it's a sphere just like yesterday, same total amount of charge and everything, but this time what we went through this whole bit of English to realize that in this case now, this time I'm saying if it's stable, then all the net charge will be all on the outside. If this is metal, again, if it's plastic, you could put the charges wherever they want and then they'll just stay there. So you could put them on the outside if you want, or you could put them everywhere and they'll stay there like we did yesterday. If it's metal, I don't care where you put them. If you let enough time go by, all the charges, don't make me hit, all the charges will be on the outside and stay there stably, right? And therefore the field line diagram for this, for a conductor, is just exactly as different as it could be from yesterday's. The field lines will look like this. Then I should have given myself more room. The field lines won't start at the center. Okay, wait a second. Looking at the chat. Oh. Yeah, okay, so Q stands for net charge. Q stands for the given number of like extra protons that are sitting in this arrangement. So, and that's what Q always, so Q stands for charge. If it's lowercase q, I mean some amount of charge that we're looking for, trying to solve for, or don't know. Generally, if it's lowercase, I mean something about it we don't know. But if it's capital, it's a number. So like capital Q here in this case could be like +3 coulombs worth of extra charge, which in English really means like there's like 3 trillion or something extra protons in this ball because we've arranged that way and we've taken out the electrons and put them somewhere else. So that's what Q means, is net charge, okay? And it's functioning in this context the way mass would function in a gravitational context. But so I'm saying like, so in some, I'm gonna copy the same thing again, just, God, that keeps, all right. I.e. the insulating sphere from yesterday looked like this, the field line picture looked like that's the insulating sphere from yesterday, and we solved it. We did the field inside and outside. Now what I'm talking about today is the conducting sphere, field lines. And today, the difference is that it looks like this. I mean, this is the fundamental. And of course, you know, like I live in reality too, sort of like you guys. I mean, I don't live in a world of perfect spheres or perfect lines, and there's a way in which physics can sound very like, why are we always talking about these perfection cases that have nothing to do? But don't think of, it's not so much that we're talking about perfection, it's that we're talking about pieces, right? The idea of physics is that I'm analyzing a sphere and then I'm later going to analyze a line and then a plate, because if I get the fundamental pieces, then I can put them together and understand reality. It's not that we're trying to pretend that reality is this simple, but we are saying if we skip this fundamentals, then we'll never understand reality. Oh, sorry. Let me look at the chat. Wait a second. Right. Okay. So these two private chat questions. So this is my point, right? I'm totally saying, like, if there's one takeaway of all of this right now, it's that the difference between an insulating sphere and a conducting sphere is that the field lines in one case will come from the center and in the other case they won't. And so that is what I'm saying. And someone just asked me why. Yes, okay, well, in a way it's a big long explanation that I'm like trying to give for all these 45 minutes, but largely I just can't use technology. Okay, but the main reason I'm saying is that in an insulating sphere, you could put, when I say insulating, it's shorthand for an insulating sphere where we put the charge everywhere, okay? It's possible in an insulating sphere, you could put the charge wherever you want, and wherever you put it, it will stay. So insulating sphere is shorthand for of an insulating uniformly dense sphere. That's really what I'm saying. And in that case, if there's actually charge everywhere, then there's field everywhere. But in the other case of the conductor, I'm saying, I don't care where you put your charges. If that thing is made of metal and you place your charges wherever you want, but like walk away, and because it's made of metal, the charges are going to start moving around. They're not going to hold still. Where they're going to end up is all on the outside if it's a conductor. That's the part that I'm trying to explain. It takes a little while. Why? But that is what will happen. If it's a stable conductor, all the charges will end up as far apart from one another as they can be, because only in that spot will they stop moving. Only in that spot will they not feel the forces of one another to accelerate them. So the difference is this diagram that I'm drawing, that yes, right. So for insulating charges on the inside, or at least can be all throughout, and yes, and will be in the context of our exams. And for a conductor, you can memorize this. I mean, I hope you understand it, but for a conductor, for a stable conductor, charge is always uniformly distributed throughout the surface, not the body. Because the circle is, I'm just looking at these chat, I'm just trying to, yes, because the circle. Oh, the circle, no, the circle itself is like an actual object. Like in both of these cases, I have a ball in the lab, like a globe in the lab. In case one, I've made the globe out of glass, let's say. or plastic. And in the other case, I've made the ball out of metal. So these are real objects, these circles. And then I'm saying that these real objects that have lots of protons and electrons already in them, like because they're made of atoms, I'm saying that we deliberately like charge them up or charge them down, however you like rub them with socks from the dryer. I mean, I actually am saying that, like as silly as that sounds, like, you know, when you take two socks out of the dryer and they're like all sparky, like take one of those socks or a balloon and rub it on your head and then rub it onto onto each of these balls so that they're like charged up. The first thing I'm saying is you can do that to metal as easily or difficultly as you can do that to glass. You can. But now the difference I'm saying is if you do that to both of these balls and walk away with the metal ball, all the charge, all those extra electrons that are whatever that you just placed on it will all eventually find their way to the outside. And eventually is like microseconds. On the glass one, the charges will stay wherever you put them. Okay, right? An example of an insulating material is like glass, plastic, carbon, almost anything that's not metal is insulating in this context. But glass and carbon would be sort of the big lab examples. Okay, I think so. These are good questions, I think. All right. But now, I said all of that so that I could just do this. This is all the big subtopic we're in right now is like insulators versus conductors. It's kind of a big English mouthful to kind of get that we've now gotten out of the way. Hopefully it won't get any harder than that. But now I'm going to apply it here. I'm saying back to the conducting sphere. So back to solving ER for the back to solving ER for the conducting sphere. We're on step 2. Step 1 is drawing the field line diagram. That's all as far as we've gotten right now. Step 1 was draw the field line diagram. So here it is. Again, we're talking about the conducting sphere now. The field lines due to this sphere look like sort of that. It's supposed to be symmetric. I'm supposed to not be a spaz. This is still plus Q. Radius R. Okay. That's what we have. Now we're doing the procedure again from yesterday. And by the way, this is all getting bogged down. It's not, none of your questions are bogged down. I'm a little bogged down in myself because I'm trying to do Gauss's law to these different examples, but then I had to stop to do a conductor versus insulator distinction. But we've now done that distinction. So I'm telling you right now, I would like everybody to, follow this. But as soon as we're done with this case of this sphere, I'm going to do the exact same thing for 2 different tubes for conducting and insulating, and we're going to go inside and outside. And you'll really see it then, I think. Once you see a totally different example of the exact same idea, and I know I don't do a lot of examples in this class in general, we just don't have time, but here we will. So you really will see this, I think, if you don't yet, whoever you are, I'm just talking to everybody or nobody. So I'm saying, if you look at the notes from yesterday, we're now step 2 in Gauss's law. Step 2 is choose and draw a useful Gaussian surface at R. Okay, just like yesterday, we're trying to figure out the field at a certain location R. So we're going to use this trick of, we're going to believe that Gauss's law, we're going to use this trick of finding out the flux at R first and using that in order to get the field at R. Okay, and my internet connection is unstable. My computer therapist telling me that again. So just like yesterday, we're going to have to draw a surface at R, a container of some kind. And we're going to make use of the fact that Gauss tells us no matter what container we pick, there's a piece of knowledge we'll have definitely about that container. Like we'll know what the flux is equal to. It's going to be equal to just the charge contained within the container, divided by a constant. What we want to do is pick a container. We know it's going to work for all different shapes and sizes. We want to pick a container that makes this computation solvable. So just like yesterday, okay, it's not, you'll see this better when you see an example that's not a sphere, because it all just seems repetitious right now. But I'm saying the sphere that was given, this sphere of capital R, this is an actual metal ball in the lab, right? And we want to know, sorry, this is the actual situation. We just walked into the lab. It's like this ball, this shimmering ball of metal that has all these extra protons in it. Therefore, it's emanating field lines out from its surface. Now, we don't visibly see those field lines with our eyes, but they're there. Okay, but they're there. And Gauss says, if you're interested, says Gauss, he says, all right, if you're interested at picking some random place in space, call it lowercase r, some random space point, which is outside the whole sphere, some random point for which lowercase r is greater than capital R, and you want to know what the field is there. What Gauss says is, all right, look, draw a container there. Yeah. That's supposed to be an R. Draw a container there. And I guarantee you the electrostatic flux emanating through the walls of that container will be entirely determined by the charge contained within the container. Okay. So I'm going to pick a container shape now. I could pick a cube. I could draw a cube in my mind at this edge R and surround the whole charge ball in a cube. And if I did that, Gauss's law would still be true. The total flux through the cube would be Q enclosed over epsilon naught, but it wouldn't do anything for me. It would be a cheat that wouldn't work if I picked a cube, or if I didn't pay attention to this pick a shape part. If I picked a cube, the total flux, I'll say this. I'm just going to quickly show you like what it means, what would happen if we chose wrong, like why this actually is a choice. Right. If we have this ball of charge, and in our minds, we surrounded it, like if in our minds we put a cube at that position R, okay, this is wrong, bad choice. This would be a bad choice. Here, if we had this ball of charge and we surround it, we enclose it with a cube, what's bad about that, or like why it makes a difference is we could do that, and the thing is, even if we did that, the law would still be the law. Even if we surround a ball with a cube, yes, it's still going to be true that the total flux emanating out of that cube would be the total flux, the total left side of this equation would be exactly Q enclosed over epsilon naught, which is what it is going to be when we make a good choice. But what I want everybody to see is look at the field lines. Like the field lines go like this. The field lines don't hit the surface of a cube the same way everywhere. That is the key. Like, Come on. Okay. If I surround a ball with a cube, Gauss's law is still true. The total flux will still be whatever it always is, but E will not be constant with respect to ds. If I pick a cube, there are regions on the that I'm looking at everywhere in the inner surface or the outer surface of that cube, the cube itself. And there's some places where the field lines are very close to each other, and there's some other places where the field lines are very not close, like because there's corners to the cubes, and there's some places where the field lines are hitting the walls perpendicularly, like right here, but other places where they're totally not, like up at this corner. Does that mean the law is wrong? No. Does it mean that could I still solve the integral? Well, maybe somebody could, but somebody would have to in order to get E, which is our goal. Our goal is to solve for E. Gauss's law does nothing for us if we pick a bad shape. It only does something for us if we pick a shape for which we can take E out of the integral and not actually have to do it. That is the surprising joke of this whole affair, is we're going deep into understanding integrals so that we don't have to compute them. This is the difference between a physicist and a mathematician in a way, although Gauss is one of the greatest mathematicians of all time. But he loved to figure things out so as not to have to do work. Like that's what he's famous for, is coming up with ways not to have to slog through computation. So I'm saying we're not going to surround this sphere with a cube because it won't allow us to solve for E, which is what we're trying to do. We're instead going to do just like we did yesterday. Like once you know all this, it's easy to do. We're going to make a good choice. Make a good choice. We're going to enclose the ball of charge with another ball, with a sphere, okay, with a Gaussian sphere, which really technically means the surface area of the sphere, with a Gaussian sphere, just like yesterday. No difference. We're just going to get different results. I don't know what I mean by yesterday, really, but so I'm gonna do this page fast because I didn't really say anything here anyway. I'm saying just like yesterday, here is now our charge ball. And this time it's conductor, so all the charge, I'm always just assuming positive charge, I mean, these could be electrons as well as they could be protons, and then all the field lines would just go the opposite way. We have this. And I'm looking for the field like at some distance r, right? So whereas this was r. And so I'm going to draw a Gaussian sphere as not a cube at this r. This is starting to get confusing. I mean, it's all abstract, but you're abstractly supposed to be picturing that we walked into and looked at a concrete actual ball of actual protons. Now, and we're interested in what's the field nearby that ball of protons, like a few centimeters outside of it. So in our minds, we draw this Gaussian sphere outside it, okay? Now we're finally moving along here. Step 3 of the Gaussian procedure says verify, like look at my diagram and make sure that I believe in my mind that all the field lines would hit a sphere with the same density and with the same orientation as every other spot on that sphere. I already verified this yesterday. Like we're talking about a ball within a ball again. Same, in other words, this is the same field line picture as yesterday. It's just the arrows start in a different place, but the arrangement of arrows has the same symmetry properties as yesterday. So yes, I'm saying yes, I picked a good shape. I'm saying E is a constant along this shape. It's not a constant throughout space, but it's a constant throughout the surface of a sphere. Therefore, step 4. Therefore, step 4 is we write down Gauss's law, okay? Double integral, double closed integral, E dot product, yeah, Oh, dot products. They're so dot producty. And you cannot quote me on that. Okay, this is the law. Takes getting used to it, but I'm writing it down just like I always write down F net equals MA when I'm using it. Here's the law. It seems to me, I just verified visually that neither the magnitude nor the direction of the electrostatic field is varying as a function of ds, as a function of area, right? Therefore, because of step 3, because of all my conceptual work that I put into step 2 and 3, I can say this, and this is the key, do all that conceptual work to get out of the mathematical work of integration. And this so looks like cheating, right? But it is so not cheating, because honestly, I could definitely tell you, when I first saw this stuff, it meant nothing to me. I could tell you more detail about that, but believe me, when I first saw this stuff, it meant nothing to me. And I thought I loved physics at the time. I was signing up for physics, and this stuff like I did not fit in my brain. Eventually it did, because eventually I got myself to understand integrals, but through this, like this way of not, you can only get away with not doing integrals if you, once you cross the barrier of understanding what it is that you're getting away with not doing. You have to understand why you can take the E out of the integral, but the reason is the shape that we chose. So we have E double integral ds equals q and cos over x. I'm not still looking just like yesterday, for sure. I'm just writing again. We have this. But the integral of ds is like the integral of dx equals x, right? The continuous sum of all, the whole is equal to the sum of its, yeah. So every time I say Gaussian, I'm trying to signal two things. One, I'm trying to signal that it's imaginary. I mean, it's hypothesized. If I say a Gaussian container, I mean a container in your mind. But also by Gaussian, I mean that I'm actually only talking about the surface area of whatever that thing is, right? A Gaussian thing is a closed surface, okay? And the double integral of ds is the total surface area of that. It's the sum of all of the infinitesimal s's, and each bit of s is a bit of surface. So just like yesterday, it's a sphere. And the radius is not capital R, the radius is lowercase r, like it's always of the shape that you made in your mind, which you always make at the position in space of interest, which we call r. So radius lowercase r, right? So I'm saying, I might be, so I'll read this out loud so I can go to the next page. This says total surface area of Gaussian container. Here, the surface area of a sphere, radius lowercase r. I could see why nobody actually consults these. I can't read my own handwriting either, but so I'm saying, so that's 4 pi r squared, we said yesterday. So we're saying again, just like yesterday, E 4 pi r squared equals Q enclosed. Okay, now we're almost, sorry, yep. Okay, back here, I'll just say something about this. We're about to get an answer for outside the conducting sphere. Again, we've done case 1A, 2 parts, and case 1B, 2 parts. I'm sorry. Yesterday we did case 1A, the conducting, I will say this again. Yesterday we did case 1A, the insulating sphere. We did 2 subcases, outside the sphere and inside. Now we're doing case 1B, the conducting sphere. NP looks so much like no, but it actually means an NP. Here we're doing the conducting sphere. I'm about to go inside and then go outside. It all looks the same as yesterday because it's a sphere again, but the results are about to be different in detail because, all right, well, about to be, if R is indeed greater than capital R, which I'm saying right now, for outside, then Q enclosed, well, I mean, Q enclosed always means all of the charge enclosed by the Gaussian, i.e. imaginary shape. This, should I just, this always, Q E N C, that's supposed to be parentheses E N C, means enclosed. Q enclosed, and please always include that. If you just start writing Q for the right side of this law, you'll miss the whole point. Like, it's not that again, you'll just miss the point. It's not any Q, it's the Q, the charge that's enclosed, that's embodied, surrounded by, enclosed equals to all charge, all net charge enclosed by the Gaussian surface, or in other words, all the charge contained in the Gaussian container. Okay, that's all we're supposed to count on the right side. That's entirely what we're supposed to count on the right side. Here in this case, if R is greater than R, close. Oh, great. All right, I just got a question in the chat. A great question in the chat. Wait, oh, sorry. Right. Okay, great question. Okay, so the answer to what Q enclosed is totally depends on where we're looking. If right now I'm looking at that lowercase r is greater than capital R, if right now, again, remember, here's our charge ball, but our Gaussian surface is somewhere outside the charge ball right now, just because I happen to be doing that one first. Like, what I really need is more of me. Why does this keep happening? Okay. If we're really outside the charge ball, so we picture you walk into the lab, there's a proton ball there, a ball of protons there. In your mind, you surround the whole thing in a Gaussian spherically shaped container because you're interested in what effect is this proton ball having on its outside environment. So in your mind, you draw like a sphere outside it. Well, I'm saying if we're outside it, then our Gaussian sphere has contained all of the charge, like all of the charge. Someone in the private chat is making a great insight. It totally is the right connection. I just want to tweak it slightly. I've been spending all this time saying that all the extra charges in the proton ball, all the extra protons, went to the outside of it. And they did. They're all on the outside of it. They didn't fall off, though. They didn't fall off. They're just all on the outside. So if we are surrounding the whole thing with a much bigger sphere in our mind, then we will enclose all of that charge, all of it. In other words, I'm saying, oh God, I'm totally ultimately agreeing with the insight of somebody in the private chat, but I want to make absolutely clear, I'm saying that if, in this case, if R is greater than R, then the Q enclosed is all of that entire given constant Q, capital Q with the plus sign, right? If we're outside, in other words, if we're outside, then E times 4 pi R squared equals plus Q over epsilon naught, okay, if we're outside. And therefore, for like you're going to maybe not be happy when you see this. I'm saying that then if you're outside, a conducting ball, the impact of the conducting ball is just precisely identical to the impact of an insulating ball. If you're outside, the entire field acts just like there was just charge right in the center of that ball. If you're outside, so far I'm saying that this could seem really boring. It seems like I'm saying the same thing 3 times in a row, I am saying that with 3 different questions, we are getting the same answer. I'm saying that whether you look at the electrostatic field from outside an insulating ball, like a carbon ball of extra protons, or you look at the electrostatic field outside a conducting ball, like an aluminum ball with extra protons, you'll get the same field either way. And in both cases, it's the same field you would get if you were just outside some point, some literal 1 proton itself. Because in all 3 cases, the field line diagram is the same. It's a bunch of radiating arrows, like radiating out equally in all directions. In all cases, you'll get equals an inverse R squared function in all 3 cases. To emanate a magnitude of field that gets weaker and weaker as a function of R squared is to emanate a field equally in all directions. A point does that, a sphere does that, and a sphere does that. Whether all the charges are, in other words, this is just like gravity. Whether you have a shell or you have a solid, if you're outside it, it makes no difference. The field lines that come from it are just the same as field lines that came from the center, either way. But if you go inside, if R is less than R, oh yeah, yes, I'll try. Okay, I see this question. I'll try to get that in a second. But the difference, I'll try to explain again what epsilon is, but it is just a constant, like literally the thing with epsilon. I will say more about it. I really will. And I know that it is sitting there being annoying. But the thing about epsilon is just like big G in the gravity equation. You don't want to worry too much about it because it's only there to keep all of our answers consistently in meters, kilograms, and seconds. Like literally, it's possible to do all this physics without the epsilon there at all. And that's the way Gauss did it, actually. You could just set the epsilon equal to 1 and you wouldn't have to worry about it at all. And all the physics would be the same. It's just that your answers wouldn't be in standard metric units. That's all. So the one thing to say about the epsilon for right now is it's just a number that converts everything into metric units. And I mean, and it just happens to be this number. Like it is a number, but you totally don't have to memorize it. You just have to understand that that's what it's doing. Oh yeah. No, blah, 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 blah. Wait, I was doing this wrong. Right. So don't memorize it and don't worry too much about epsilon. Now, as to the difference between lowercase r and capital R, again, that's something we really want to get increasingly used to through the whole course. Like in general, lowercase r is the variable. It is the independent variable of what we're looking at. We're looking at field as a function of lowercase r. Lowercase r means is displacement. It really means displacement from the center of some charge shape that we have. So in this, so r measures from the center of the charge ball, but lowercase r is always like the place in space that we want to know what's the electric field there. Lowercase r point, lowercase r sorry. Lowercase r, and this is lowercase r is going to be a displacement vector. It's the displacement from the center of whatever charges we're talking about to some arbitrary point in space that we are asking what's the field there. And it's arbitrary in that what we always believe is if we could find out what the field is doing at any one arbitrary point in space, like if we could write it as a function, well, then we know what the field is doing at every other arbitrary point in space. So lowercase r points to the place of interest, the arbitrary point of interest in space. Many people call that the field point, the point where you want to know what the field is. It points from the center to that. Capital R is literally just the radius of the ball of charge that we're dealing with here. Capital is a constant given thing. It might as well be a number. It just like happens not to be, because we want this to apply to all different examples. But capital R, think of as a given number, and lowercase r, think of as an independent variable. And that's kind of but they're both measured in meters. They're both distance. One's a displacement, the other's a distance. The other thing is R by definition does equal R, the displacement vector, equals the distance R times a unit vector pointing from the charge to wherever you're looking. And I know that, that's why all the vector stuff comes full circle in this class. Let me just say to everybody again, the thing that hung me up forever in doing physics was the R business. I didn't get R forever. Okay, I really am sympathetic that it does not, even if I say it in what I think is the perfect way, it doesn't make anybody get it. You have to kind of, that's why the more you can put me in the background of your life, not me, but any physics, like when I say that you got to watch these lectures, I can't imagine actually I don't even want to hear myself this long. Nobody can watch these lectures. But if you just have some of the stuff in the background and you start hearing about R over and over, you get used to eventually what R is. And I want everybody to. But that's why people can, again, someone can ask me tomorrow what R is, and I'll still be sympathetic and try to answer if I can, because it takes a while to get used to. I didn't get R forever. But it is just the displacement. It is the displacement from the center of the charge to wherever you're looking. And trying to find out the field. And our goal is always to look somewhere in space and know the field. So I'm saying then if, oh my God, have I looked, oh, okay. If R is greater than R, we said the field function we found using Gauss's law is nothing new. It's the same field function as outside an insulating ball or outside a point. But if R is less than capital R, if lowercase r is less than capital R, i.e., if we're looking at points within the charged ball, so this is still R, and the field lines are, and the field lines are still doing this business. But now we're looking like somewhere there. Okay, so that's the only difference in that. That's why this is still the same case situation, but now we're looking inside. All right, it's all the same procedures. I'm going to start accelerating now a little bit. It's all the same procedures. It says step 1, draw the field line diagram. Okay, we did. Step 2, choose and draw a Gaussian surface. Okay, it's going to be a sphere again. I think people are maybe starting to get that. So I'm going to draw a Gaussian sphere, but I'm going to draw it at R, as always, and now R is inside, so I'll draw a Gaussian sphere. In effect, I'm doing step 2 right now. I'm choosing and drawing a Gaussian sphere. I'm putting it inside at R. Step 3, I'm verifying. Yeah, it looks good again. I don't think, well, this is a weird thing to say, but I can't find any spot on this surface where what the field lines are doing seem any different at all in orientation or in density from what they're doing in any other spot. I think, again, I've picked a good shape because I think, again, the E field is constant. Now, why do I think at this time? I think at this time because I think it's constantly 0, right? I'm not trying to trick anybody. I mean, no matter where I go on this thing, it doesn't look like there are any field lines at all from my picture. And there aren't, in fact. But still, it still verifies I think I've drawn a good shape. Maybe other shape might have worked also. But it appears that I can now do step 4, which is write down Gauss's law. This time in yellow. I don't know. I'm obviously being completely inconsistent with colors here. But. Okay. Also, why is... I don't mean to, I don't know if that's, oh, okay, sorry. So again, we have by verified. So now I'm doing in my mind, that's step 4. I just wrote down Gauss's law. Now step 5, I'm solving. So the E comes out again. And I have this. And again, The total surface area of the sphere I drew, again, is 4 pi lowercase r squared equals q enclosed. And now here's where the private comment totally, and I'm going to say, just because I think it really was such a fast insight, it showed someone was definitely paying attention named Jessica, when she pointed out earlier that like now here at this step right now, if R is less than capital R, if I'm inside the sphere and it's conductor, we've just been arguing for 45 minutes that if it's a conductor, there ain't no charges there inside the sphere. For a conductor, we're saying this is 0 if stable conductor. Right? So here we can see in the picture, our Gaussian surface does not enclose any charge at all in this situation. Sorry. So I'm now saying, if you like, this is case 1b sub 2, right? This is now case 1b, the conducting sphere, but now we're inside the sphere, and we're saying that the result of the electrostatic field at any point inside the sphere is zero. Just like the, anywhere inside is 0. This is like anywhere inside a mass shell, the gravity is 0. I'm just showing it a different way now. But like we have to be careful. I'm saying we've got this metal ball in the lab. It's a metal ball. It could be metal all throughout. It could be a solid metal ball. But it's been sitting there for a while. I'm saying if we go to points within the solid metal ball of this, we're going to get a field of 0, because even though the metal is solid all throughout, the charges, if it is indeed metal, then all the charges are on the outside. So what we have here, we might have a solid bit of mass, but we're really somewhere in the inner regions of a charged shell, just like we talked about with gravity back in the day. So the field anywhere within the conductor is 0. Gauss's law is showing, but of course my picture already showed that. Like if I'm following myself, I kind of already knew that even looking at the picture. In fact, because the picture says that all the charges are on the outside. And the reason I believe all the charges are on the outside is because eventually, if they ever did happen to land there, that would cancel the field and stop them from moving. So in a way, we're just reinforcing in a sense, or making it rigorous, a set of beliefs that we might have started with. I'm not sure what beliefs you started with, but I'm saying in some so far, because we still are, again, none of this made sense to me until at least I saw the next shape. All of this seems like the same answer over and over again. You can't tell what I'm saying that's new and what's old, but when I do the next shape, which I'm about to do, then I encourage you guys to go back and study and look at this in contrast. But what I have so far, thus far, but can I say again? No, I won't. I'll say it in a minute. But thus far, this is all given some net positive charge of plus Q. So these are all positive. So thus far, I'm saying case 1, outside a sphere, the electric field acts just like a point. Inside a sphere, the electric field is linearly proportional to displacement, right? This is case 1A, the insulating sphere. If you're outside, it acts like a point. If you're inside, it acts like plum pudding gravity. That's the insulating sphere. Case 1A, 2 subpoints 1 and 2. Case 1B, I'll go back to that page in 1 second. On case 1B, the conducting sphere. If R is greater than R, then E equals. And if R is less than R, oh, okay. This is a summary of all the results of the cases we've done so far. Once you see the picture, it's a nice schematic picture. And yes, totally one question on the exam is going to be like about this, but if you just memorize these answers to these cases, it won't help you. Like this doesn't, it doesn't mean anything. But if you start to see, if you can see how to derive these, then you're in shape. Okay, so far, and I'll just go back to this page. I'm sure I've got this. So if you're outside, both results are the same. Outside insulator, outside conductor, both cases you feel like you're outside a point. Inside insulator is like being inside Earth gravitationally, and inside conductor is like being inside a shell. It's nothing. Okay, that's what we're saying so far. Yes, now on the exam, would you have to worry about a different shape? Here's the good news and the bad news is yes, but the bad news. So on an exam, I just gave you, in effect, 4 subcases of a sphere. On the exam, might you have a different shape? Bad news, yes. Good news, I'm about to do that shape right now. You won't have a shape on the exam you've never seen. I'm going to do them all right now, even if there's nothing else that I do. And there aren't that many shapes. There's 3. But okay, and again, you'll know, when your first year understanding is tentative, you'll try to understand this case by case, as you should, and you'll try to memorize certain steps that aren't sinking in at first. But you'll know you really get this once you see that all the steps, that I'm just following the same procedure. Like, you'll know you get this when you could figure out any new shape on your own. But it won't be a new shape. It'll be one of these. This was the sphere. Now we go to lines and tubes. You'll see, to lines. Okay. So case. I know I'm going a little bit fast. But also the other thing is, why am I talking? I love teaching. I love all this. I've been doing it a while. I don't have any illusion that just because I say something, that means that it means something to somebody else. Like, teaching is not me saying and you hearing, right? What I'm saying is I'm just trying to direct your attention to what you need to figure out when you have a moment to breathe. Like, all these notes are for you to look at and then try to make sense out of. I have stories about that too, but I can't imagine this all adding up perfectly right now as I'm saying it. You need a chance to see where it doesn't work and stuff. Anyway, so here's the next case. Case 2. Case 2A. Line of charge. Oh, and luckily for this one, well, yeah, okay. Line of charge, insulating material. So this is not quite yet. This is almost a wire, right? It is like a wire, but it's not a circuit. It's not a wire with charge rushing through it the way you have in lab. This is just a bunch of charge sitting there in a line. Okay, so we're talking about like a line of charge for which the density of charge we're going to assume that the density of charge here is a constant. The number of coulombs you have per unit length, per meter, we're going to assume stays constant. So I don't know how long the line is. It's very, very long. I don't know totally how much charge is, but I know how much charge there's per unit length. Sorry. We're going to assume it's extremely long. How long is it? Like, what do I mean by extremely long? Like, how long is extremely long? This is what I mean by extremely long. I mean that you know, once I set up the question, what we're going to ask is if you go to some distance near that line, to some point, a distance r away from that line, we're going to ask what is the field in magnitude and direction at some field point, at some point in space displaced from the line, a distance r, right? When I say that the line is really long, what I mean is assume that the total length of the whole line is so much longer than any distance. When I say the line is really long, I mean compared to any distance that we might ever measure walking away from it. I mean that the length of the line is enormous compared to whatever distances we walk away from it, such that we're assuming, question, John, or anything? We're assuming that wherever you look in this line, I feel you're in effect in somewhere in the middle of the line. It's like assuming wherever you are on Earth, wherever you are on Earth, you don't see, well, that's a bad example, forget Earth. But you're on this line, and I'm saying it stretches out in so far in either direction that when we want to know what the field is, like a centimeter away from the line, we still can't tell where the ends are so far away that they don't make any difference in our calculation. Wherever we stand, we're basically just amidst long line. Okay, and that's very realistic. Again, nothing is actually infinitely long in the real world, but in the real world of a lab, it's very easy to pick up a wire that's like a meter long and have that be so much longer than any angstrom away that you're taking a measurement that the angstrom away makes no difference, like won't even show up on the same instrumentation, right? That's what we mean by this, okay? Therefore, so given all the above, so we're going to find the electrostatic field. Now, the electrostatic field, due to a line of charge, we're going to find the electrostatic field at some field point, at some location, a displacement r away from that line. Like totally the same problem as we just did with the sphere. Hopefully people will start to see that. It's the exact same problem. It's a different case. So we're going to do it the same way. We're going to do Gauss's law. And now, and anybody who's still with me, and this is again a lot, but if you're still with me at all, and that doesn't mean you fully get what I'm saying, but if you're still like trying to hang on with what I'm saying, then you'll like this, I think, because this is the problem that I'm going to do now that you would be afraid I would suddenly surprise you with on an exam or something. This will be just different enough to really show you what the larger procedure is, and it won't run you into a circle like the other thing. So let's see. But again, I won't surprise you on I mean, either this will be on the exam or the last one, whatever. So what I mean is follow the procedure, follow the Gaussian, follow the steps for the Gauss's law procedure. That's what I'm going to do right now. Okay. So step one is draw the field lines. Possibly the hardest step of the whole thing and the most important, the one that people would skip because they would think they wouldn't know how, but let's do it. So step one, draw. But it makes all the difference. And it's not as hard as it's never as hard as it seems like it would be. Draw field line diagram. Draw the. Okay. So this is a charge. That's not the field lines. That's the situation in the lab. And it's going on forever. It's got a line of charge whose density is constant. What are the field lines going to look like? Well, look, a line is made up of a bunch of points. I think I actually said this once, but a line is made of a bunch of points. Each point is going to radiate out in all directions. So like this point here, we'll make field lines that go like that. Right, that's random. And then another random point, let's say over here, we'll make field lines that go like, it all begins with points. And we just add up points and we make reality is the idea. So each of these points would individually make this field line, these field lines. And then we believe in superposition. So we believe that the point number one doesn't know that point number two is there. Like its arrows don't change as a result of point number two, but the net effect does. That is, we've got an up, we've got like this arrow and this arrow. Like, let's say that right at this point, if I were to look at this point in space, I'd be pushed up and to the right by the yellow dot over to the left. Hold on, I'll get the chat question in 1 second. I'm saying if we look at this point here, the net result, we have an upright, we're being pushed up and to the right at this blue point, and we're at the same exact time being pushed up and to the left by the same amount arrows, because everything, I mean, I just picked two random points that are both doing the same thing. So the left and right cancel, and what's left is the up, right? Any point here. And I can make the same argument for all these arrows. In other words, what I'm going to end up with, the field lines are going to end up looking these are the field lines okay, these blue field lines that I'm drawing are spokes, meaning that they look like they're parallel to one another, but they're not really meant to be. This is meant to be like, look at the line of charge as a long caterpillar, and the field lines are like legs coming out of that caterpillar. If I looked at it dead on, I would see this. I know I've drawn this once before, but in other words, a line, if you arrange a whole bunch of points in a line, then each point will radiate out equally in all directions. Every single point will. So the whole thing will end up radiating out in all directions, except for that direction that the line is itself, right? If a point has zero, well, I'll get to that. But right, so these are spokes is what I'm saying. Let me just, there was a chat question, hang on a second. I don't actually, all right. So I am getting one question in the chat, which I think is a good question. I don't fully understand it. But one thing, it says something like, doesn't the outside of the conductor also have to have a charge if the inside has a charge? I think I get this question maybe. In order for an atom to be electrically neutral, or a molecule, in order for a molecule to be electrically neutral, yes, for every bit of positive charge, you have to have counterbalancing negative charge. Most things in the world are electrically neutral. Like, that is totally true. Like a piece of paper, my calculator, my pen, my glass, everything hopefully is stable. I'm not feeling any sparks from anything, because mostly when left to accident, there's an equal number of protons for every electron in macroscopic arrangements. This is why we didn't really discover or figure out electricity until about 150 years after gravity. But there are positive charges and negative charges in the world, and the negative charges, electrons, can be moved around and they can be separated from the positive charges. So everything I'm saying in this topic of physics right now all assumes arrangements where we have a bunch of net charge, extra positive or extra negative if you want to do that, either way. But all these problems that I'm solving here are situations where there's an extra amount of positive charge, and we want to see what kind of field that's creating. If there was an equal, so if I say that there's charge on the inside and I say it's plus Q, you might say, well, then there has to be negative Q on the outside. Like if you were in a chemistry class, you might say that because we might be assuming that everything was balanced. But if everything were balanced, there would be no electric field. So I'm trying to solve in cases where there isn't balance, where there isn't balance, and I'm trying to figure out when there's not balance, what kind of field does that create in the world? So I'm not sure if that answers or not, but there isn't. there isn't going to be a balance of charge in any case, except by accident or something. And then when there's a balance of charge, there's no field to study. So we are assuming they're unbalanced. I don't know if that's why I should always be saying net charge is what I mean when I say that there's charge. I mean extra charges. But okay, so the field lines from a line of extra charge are spokes like this. That was, I just drew the diagram because I'm going to use it now to get my answers to solve for Gauss's law. Okay, so step 1 was draw the field line diagram. Step 2 is change the color. Step 2, and for anybody who's tuned out for the last 40 minutes, I don't blame you at all. Like if you've gone, I don't blame you at all. I totally sympathize, but I would pay attention here. What I'm about to do is the point that might clarify everything, because now I'm going to draw a Gaussian shape. Step 2 is choose and draw a Gaussian surface. This is always the next step, and always at the place of interest, at R, at that field point in space. Okay, this is always the next step, but now for the first time ever in all of this, I'm not going to draw a sphere. So you'll finally maybe see what larger point I'm trying to make. I mean, many of you do. I don't mean you'll finally see. You know what I'm saying? Maybe you don't. I'm saying, here's our line of charge. Here's our field lines. I'm now drawing the same color just because I wanted to. So here's our field lines, right? They're spoking out. Oh, and by the way, at the ends, something weird would be happening. Like I'm saying the field lines look like this. And if you are following me, you might realize that, well, by my argument, like at the ends, the field lines will be doing something funny like that. And that's true. At the ends, it's called fringe effects. The ends will always be different from the inner regions of something. But that's why I'm saying, assume this line is really long and we're never anywhere near the ends. Okay, and again, in the lab, that's totally is a fair thing to assume. Oh, didn't mean to. Well, anyway, I'm saying we are assuming now we have our field lines. So now step 3 is choose and draw. Step 2, the one we're on, is choose and draw a Gaussian surface that would make sense for the situation. I'm not going to draw a sphere. I could draw a sphere and Gauss's law would still be true. But look, if I try, I won't do it. But if I try to surround, if I try to enclose this line, and granted, again, I don't care about the ends. I can cut off the ends because I know the density of the line. But if I try to capture it in a sphere, all these arrows, these field lines, are not going to slam into the surface of the sphere all the same way. Some of them will hit the sphere perpendicular to its surface, and some will be grazing the surface, right? What I'm going to do is I'm going to surround it in some kind of cylinder. Or tube, if you like, same idea. I don't know why I put this in quotes. We're going to choose a tube or a cylinder. And we're going to go like this. Oh, sorry. I'm sure someone, well, it just says, let's not choose a Gaussian sphere. Let's choose a Gaussian cylinder. Oh, and I keep writing, that's a good question. The reason I keep writing lambda equals lambda, like I keep going like this, I'm trying to say lambda equals lambda naught. And that is a convention I follow in a lot of these. I might have been doing it in the first exam on something and people might not have even noticed. If I say that something equals something naught, what that means is it's a constant. That whatever the first value of it is always that value. It's a shorthand way of identifying. So when I write that in a case like this, I'm saying a line of uniformly dense charge, a line, it's my way of saying the density is not only something that doesn't change, and it's therefore reliable. But in fact, I'm highlighting the fact that that's what you're going to use to identify the material and solve the problem. It's a way of, it's instead of saying mass equals 3 kilograms, it's saying density is a constant. Line of uniformly okay, that's what I mean when I say it. So now, and I'm looking at the time, okay. Oh, thank you. No, I love these. Yeah, I mean, it means you're reading, right? I did forget what I was. Oh, yeah. All right. So I've got this now. The line of charge. I'll try to keep somewhat consistent colors. Got the line of charge here, and the field lines are going like this. And again, I'm in my mind. This line is just going on forever. Let me try to make that clear. The line is just, it's going on forever. It isn't really, but it's going on so long that I don't know what's happening at the ends, and I don't care. I'm just picking a representative region in the middle where the field lines are all doing the same thing like this, right? And then what does that mean? Someone's here? Someone? Okay. And then I surrounded this line in, or I'm going to choose a Gaussian cylinder at make it a little bit smaller. Just like in the other case, I'm putting a shape, a container, right at the lowercase r, right? I'm putting the edge of some shape in my mind right at the place in space where I'm interested in measuring or predicting field, at the field point, in other words. Here, I'm making a cylinder rather than a ball. And if you don't already see why, you'll see why in a second. But the main reason is this cylinder is doing a better job of mimicking the symmetry pattern of the field lines than a ball would. And you'll see that too. Again, the cylinder is not going to enclose all of the charge of the whole thing. I'm going to lose like the ends, but that's okay. It doesn't matter. I don't even know what the total charge is of this whole line. I just know its density. And that density, I'm not chopping off anywhere. Like the density is the same all throughout. So I do step 3. Verify if I look at my picture, again, knowing this is kind of just a bad cross section of something 3-dimensional in life, but if I look at my picture, it seems like wherever I look at any little piece on the surface of this cylinder and I compare in my mind to any other piece, like up here, it seems to me no matter where I look, the number of lines that I find in that region is a constant. Like the lines don't get any more dense at one bit of cylindrical surface area than another. And they also always are pointing the same way. It seems to me if I captured this line of charge in a cylinder, those radial spoke field lines are all spoking and hitting the wall of the cylinder in the same way. That is, they're all hitting it perpendicular, right? It wouldn't work for a sphere here, but it would work. I'm sorry. A cylinder would not work to capture yesterday's sphere, and yesterday's sphere wouldn't work to capture today's line, but this cylinder does capture this line. So this is what we mean by choosing and drawing. For this case, I choose that shape. I verify in my mind visually, it looks good to me. It looks like I can now write down and then solve Gauss's law. And a good thing because we're almost done, because the class is almost done, and yada yada. Write down. And the most babyish thing that I always say is write down the law. It's like almost insulting that I say write down the law, but please trust me, it's not meant to be insulting at all. You never ever can learn these things unless you just keep writing them over and over again. And they start becoming, you can't start a problem without starting with the law, even if it seems like the most obvious thing. So you write down the law, and it really isn't obvious because who knew this law before we knew this law? So write down the law, and then we're going to solve. So the law is, okay, so this is the law. Now, if I really know what I'm doing now, if I really pick the right shape and I constantly picked it, if I really verify it in my mind, I think that shape is good. I think if I really believe that, and oh, here goes that notation again. If I believe that this is true, right? Doesn't seem like much of a statement, but if I believe that E field is a constant, that wherever it is, somewhere on that surface, it is the same everywhere else in magnitude and direction. On that surface, on that fake surface that I picked for that reason, like I picked a surface for which hopefully this would be true, then I've accomplished my main task, which is to get out of math and say, then this is true. That's supposed to be a double integral, sorry. Right? And yep. And remember that double integral of ds means the total surface area we've been saying. And here's where the pigeons come to roost right here. So now we're almost done. If we go, I'm just recopying. So I had this. So now, if it's really true that I could take the E out of the integral, and what the remaining integral is simply the trivial, the double integral of ds, which is to say all of S, which is to say the total surface area. Now I've got to put in the total surface area of the Gaussian shape that I deliberately chose, the total surface area of the Gaussian container. And this is where, like, so, you know, I could skip that step of choosing and drawing, and I could skip straight to this, as some bad textbooks do, and I could just take the E out of the integral, right? But the cheat will catch up with me. I hate to keep using that word, but it'll catch up with me because right here, I've got to put in the total surface area of the container I chose. And if I put in 4 pi r squared now, I'm totally wrong. Like everything is going to be wrong. I have to know that I put in a cylinder here. Here, cylinder. Now, the total surface area of a cylinder, well, you got to picture, like, how do you know what that is? Well, it's like asking what the perimeter of a coin is and then stacking up a bunch of coins and getting all of their perimeters added together, right? I mean, the total surface area of a cylinder is the total outside of a tube. One thing, however, well, let me put it different. One thing to notice, wherever I drew that cylinder, I'm being fast and loose about one thing in a way. I said no matter where I look on that cylinder, the field lines probably slam into the body of slam into the surface of the cylinder the same way. Yeah, unless I looked at the caps of the cylinder. This might have confused, so a quick momentary confusion might have gone through some people's minds, and then I didn't say anything about it, so then it went through their minds so fast that it might now be growing as an unconscious thing that bothers you or that might turn you off to all of this. Let me address. I'm saying the caps of the cylinder, the field lines don't hit the caps of the cylinder perpendicularly, not at all. Wherever that cylinder is like this, so it's like a tube and it's got 2 ends to it. There's no ends to the wire. There's no ends to the wire as far as we're concerned, but wherever I made my cylinder, it would have 2 ends. I want to be clear to everybody, the field lines don't spoke out through those ends according to my picture. The field lines would run parallel to those ends. It would, but fully parallel. So there'll be no flux on either end at all. Okay, in other words, actually the angle of field lines does change from body to the ends, but it changes from 90 degrees to 0 degrees. And that's the only change it ever makes. In other words, the 2 caps, each of them has a flux of 0 because there's no dot product between field line and ds on the caps. The field lines are parallel to the caps, so there's no flux through the caps. Therefore, since it's literally 0, I don't have to count it or worry about it at all. Like an integral is a sum. The whole is the sum of all of its parts. the two caps, if I were just doing a geometry problem and just asking what the surface area of a cylinder is, I would need to include those caps. But here, I'm only worried about the surface area that has flux. So therefore, I'm going to say for a cylinder, minus, so to speak, caps, the surface area. Now, if anybody wants to tell me, the surface area of a cylinder, you can figure out on your own. You don't have to memorize, right? You could think of it as what's the perimeter of a coin and then like stack a whole bunch of coins. Like let's say for a cylinder minus caps, say a cylinder of radius r and of length good, or height, you could say close, very close. Someone in the chat just did something really smart and sent it to me. I want to give that person another second to think of that through again. It's totally the right. Oh, two great questions. Wait, and I know we have to wrap up almost soon, but wait, all right. Two great questions in the chat. I'm going to pause for a second. One is, yeah. Oh, yes. Oh, okay. Wait, sorry. The reason I'm not doing a rectangle, okay, I want to give everybody a moment. Everybody, even if you've already written into the chat, like the people that wrote in the chat really fast, I'm really impressed, but there might be a little mistake in what one of the people wrote in the chat. I want the surface area of a cylinder. I don't want the volume. I don't want the volume. I want the surface area. I will actually want the volume in a step or two. So, bear with that will come up, but the surface area of a cylinder is what I want here. And I believe, and that has to be a two-dimensional concept, right? It's just got to have, if it's surface area, it'll have 2 dimensions of length in it. It means, in effect, that you think of the perimeter of one coin and then sort of multiply that out by the whole length of the cylinder. Say the whole cylinder is length L or height H, if you like. If you take the area of a one coin, and 1/4 or something, and then multiply that through by H, what you'll get is the total volume of the whole thing. So we want the surface area. Cool. I'm getting it in the chat from a bunch of, yes. There's one, hold on. And no, I just want to answer these chat questions. Give me 1 second. I'm sorry. One sec. Oh, where did? I'm very sorry. Please bear with me. Where? What? Oh, okay. The answer is yes to finish it. Yes. Okay. Yes. All right. So anybody who has tried this in the chat now has totally assured me that they see what's going on, which is great. I'm saying, and yes, we are about to finish these scenarios right here. And if there's a case 5 and a case 6, either I'm doing them tomorrow or they're not on your exam. Don't worry, one way or the. But yeah, we're about actually to finish, believe it or not. I mean, finish these. What am I trying to say? I'm saying, oh, then. Because I think we have 7 minutes, right? And believe me, we've done the hard part. I'm saying, right, so for a cylinder minus the caps, the surface area will be 2 pi r L, so to speak, if L is the length of the whole cylinder or the height of the whole thing, right? It's like the circumference, circumference extended out is what you get for surface area. Notice this will be in units of square meters, like R is measured in meters and L will be measured in meters. So we'll get something in square meters as we should for surface area. And there's a pi in there, which there better be because circles are involved. Okay, so now back to business. I'm saying thus, if Gauss's law is right, and if we chose if Gauss's law is right, and if we chose our surface right, then we have this. We have
Excuse me, Professor?
yes.
What was the
Yes.
differentiation between R and L for 2 pi RL?
Oh, great question. Wait, sorry. Oh, and I'll totally post this. Wait, sorry. Oh, wait. Oh, between L, oh, sorry. The difference between R and L is R is the distance away from the line, like to the field point, and L is like the length of the whole line. But then now that's a good, also, like when I kind of interchangeably used L to mean the length of the whole line versus L of the cylinder, that I was sort of careless about, but it actually doesn't matter either way because we can cut off as much of this line as we want. You're going to see in a second. But by L, I mean like length along this configuration, and R, I mean length away from the configuration. Does that make sense?
Yeah.
Okay,
Thank
cool.
you.
But okay, cool. But someone who also put in the chat, put to everyone, Gabrielle put everyone, right. I was being careless, like using L to label both. I really truly mean L is the length of the cylinder, truly the line you can consider to be infinitely long. But you'll see in a second why it's actually okay to be a little bit careless about that, because here's what I'm saying. On the left side, we got E times 2 pi RL. On the right side, we got Q enclosed, okay? Now, what is Q enclosed? It means all of the charge enclosed in our Gaussian surface, all the charge enclosed within the container, enclosed within the container. Well, we were never given the total charge of this line. What we were given of the line, we know its density is a constant. We know by definition, density means charge per length. Whether you call that length X or L or whatever, Q per X, we could call it. So in this case, if you want the total charge throughout the container whose length I meant to make L, I did make L, right? In other words, here, Q enclosed, is lambda times L. This is just like what we've been doing with the spheres and everything. We're always coming back to that uniform density. In other words, Q over L equals total Q over total. If I'd call the whole line a length of X instead of L, as I should have, as per Gabrielle's comment, like I'm coming back to the same thing we keep coming back to, which seems so dumb, that uniform density means stuff per space equals stuff per space. So the total amount of charge in the space of this container, L, has got to be equal in ratio to the total amount of charge to the total length, in other words, which is what we mean by lambda. So I'm saying the charge enclosed here, and I swear we're almost done with 2 minutes left to go, charge enclosed, we always have to be careful about here to write it in terms of what we know, it's lambda times L. So what we're going to get, I'm happy to go back in a second if I need to, but you might think that I might not need to. So what I have here, sorry. I have E times 2 pi RL equals lambda L over epsilon naught. So the L's cancel. That's why I was a little bit careless about them. Like I shouldn't have been. I'm not defending myself. But like the L's, as long as by L you mean the length of whatever you're looking at in the line, you don't even need to know how long the line is as long as it's super long. The L's will cancel out, and what we get is didn't need to do that. Now look, we are just about done here, and technically there's other cases, but we've really gotten over the hump here. In this, because if you can see what just happened here, then you really get how to do Gauss's law, even in a surprising new scenario that we've never done before. Here, what we're saying is the electric field outside some line, this is outside a line of charge, outside a line of charge. The electric field gets weaker and weaker as you get farther and farther away. But let me start again. If you're outside a line of charge, well, the stronger the charge is, the bigger the field, like lambda's in the numerator, as you'd expect, just like m is in the numerator of the gravity equation. And it's being multiplied by a whole constant, which looks weird, but it looks like the normal constant we normally have, just multiplied by 2. Okay. In other words, it's not 1 over 4 pi epsilon naught, it's 1 over 2 pi. Okay. It's still a constant, same units, not a big deal. In the denominator, we have an r saying that, as usual, the field gets weaker and weaker as you get farther away, as you might expect. But it doesn't get farther and farther as a function of r. I mean, it doesn't get weaker and weaker as a function of r squared. It gets weaker and weaker as a function of just r in Just about done, I swear. This is the last thing I'm going to write today. I promise. Yeah, and you've done, you can't believe how much well, maybe you can. You've all done a ton to get through all this fast, because actually what I'm saying then is, I don't care if I now, this line I enclosed with a Gaussian cylinder, because a cylinder would capture the asymmetry of this line, right? In other words, if you want to now take this out to case 2b, which yes, I'll talk about tomorrow, but like if you want to imagine that this line wasn't a line, but actually a tube made of insulating material, it'd be all the same argument, because the field lines from a tube would look just like they would from a line. If there was an insulating tube, they would all emanate from the center, just like we said yesterday. If it were a conducting tube, they would all emanate from the edge, from the outer surface, just like with the case 1A and B that we just did, right? But basically anything that you make from a line or a tube, you would use a Gaussian cylinder rather than a Gaussian sphere. And what you find is that the field, if you go to one-dimensional asymmetry, if we now have charges that are arranged along a line, in other words, we leave, in the first case of one point, it's like leaving all of space alone and just putting a point in space and saying this point is going to affect all of space equally in all directions. But then if we put a line in space, a line of charge says we're going to affect all of remaining space all the same in all directions. All the remaining space, all of the axes that are left, except for this one that we've already taken up with charge. Clearly, this line is already special because it has a charge in it. You can see a pattern that I'm saying here, that fields drop off as a function of r squared inverse when you have zero dimensions of asymmetry. If you have one dimension of asymmetry, if you've blocked off a line, an axis space with charge, then the field goes up a level, like from function of r to the -2 up to a function of r to the -1. You can imagine if I go one step further, like tomorrow, if I made a plate of charge, what will happen is we'll get r to the zero dependency. We'll get constant field, in other words. Like there's a pattern here, but I don't mean to skip ahead or anything like that. But if you get what we've done here, these are, but definitely. Oh, yes. Yes. I will. I don't care how you exactly write the final equation, but I kind of do. You kind of want all the constants together and then all the variables together. Kind of try to write it the way I do, sort of. But to very quickly, because I know you have to go to lab, I'm just looking at these questions. I will pick up from here tomorrow. I will, and there's not new homework on this or anything. Just, I would suggest you look at it, let it sink in. I will definitely post, by the way, people have been asking me, I believe so far, every single lecture I've given, I believe I've posted the notes as a PDF, maybe a couple of days later sometimes. But if any are missing, let me know. And every one of these I have made into a recording that I put on Vimeo and YouTube. And if you're not, maybe you're not getting notifications of that, I didn't think of, but they're definitely, so yes, I will post this as soon as it's ready tonight. Everything as of yesterday has been posted. I mean, the fastest thing, just go to YouTube and type in maybe people don't know this, but everything is there. It's like the one thing I've sort of done right. If you go to YouTube and type in into the search bar, like the channel, I didn't name this, it came automatically through the Vimeo thing, but the channel is called Professor Yaverbaum, and it's all there. And of course, I would love it if anybody would, whatever you're supposed to. I appreciate that some people have actually put likes or something with the checks, but the main thing is I can't see if you've seen them or not. So yes, this will be posted in a couple hours on YouTube. All the lecture notes I'll put in your Google Classroom. Definitely. I will pick up from here tomorrow, and I'll try to slow down a little bit. I can't slow down that much. But I can also promise you this, like, because I like the questions I get and stuff. I'm trying to get to the end here because the end is so satisfying, and we are very much on track. We're actually usually I'm much more behind than this, for whatever it's worth. We're going to get there. But whatever I don't say in class, I'm not putting on the test. Okay, there's no point in trying to slow me down for that reason, but I promise you, I think I'm going to do one more case tomorrow. But if I decide not to do the case tomorrow, then, and that case would be plates, then that's not on the exam. Okay, so right now, it would be fair for me to put something with spheres or lines on the exam, but yeah, okay, I'll stop there. Okay. All right, so I'm going to try to take all these suggestions. Some of you still haven't gotten exams back. Again, I apologize. It's not based on anything. The order is largely random. You'll get them back. You'll get your homework. You may never literally, your homeworks will get back, in a weird moment, but you'll get them back and they will definitely be counted. You can still hand in homeworks and still get credit for them. What else? I will try to do that thing that I hate, or I'll try to make a chat stream in Google Classroom for questions about the exam. Yes, and now about return things. Wait, yeah, I know everybody has to go to lab. Questions, yes, I could try right now to do a really quick question about midterms, but I think I want to do a larger office hours for that or something. Like I want everybody to know, everybody has an opportunity to negotiate or question or understand their grades better, definitely. And I am actually a softie in negotiations sometimes. Like I will give back points. It's not about that, but there's a huge time crunch. That's the problem. So let me say this. Yeah, if people can ask a couple of quick questions about what grade they got back right now, I'll try. But if I cut you off, I'm going to make maybe it'll, and I know these have to be private. Somehow, let me think about how I can make a quick little office hour thing or like Zoom office hour thing where people could privately ask a question about their test, because you do deserve that. And I do make mistakes. I'm just concerned about time. So yes, right now, if you have quick questions about your midterm exam, hang on and try to ask me now, especially if you can ask in a way that doesn't make other people uncomfortable. So I'll hang out for a bit, but I know most of you have to go to lab. So, oh yeah, breakout rooms would work. Right. Breakout rooms is a good idea. I don't know how they'll solve it. Let me think about that. Like they will definitely solve a big problem. It's just when to do it. But okay, so for right now, anybody has quick questions about how I graded their exam? Or certainly the person that just asked me.
Yeah, I can just ask now. I mean, I don't mind if people hear. I guess I was just wondering, for some of my responses, I lost points and I wasn't really sure why.
Right.
So
Yeah. Right.
I'm more concerned about, like, for the final, I want to make sure that I'm doing what you're specifically looking for.
Right. No, that totally makes sense. It's totally fair. And we can look at maybe one of the examples right now, but in general, and I don't know if you saw, I will try to post a more extensive, more clear solution sheet, but I did post some solutions that sometimes help, but it's true. If you lost points somewhere and you're pretty sure that the answer is right, which may be, and you don't know why you lost points, it may be for what I consider to be skipped steps of justification or work. But let's see right now, for example, could you give me what, if you truly don't mind doing it.
I'm thinking the questions I'm thinking about are the free body diagram and question C. Okay. But I see the very last question, but I see for the very last one, like the argument that steps were skipped and not shown. But for the free body diagram, I don't understand why.
All right, no, that's fair. And especially, and that's also maybe I don't remember if I had you for fit. Okay, so with the free body diagram, you're talking about for the pendulum one, right?
Yeah.
Is it possible that in your diagram you have an arrow for mg and an arrow for mg cos theta and an arrow for mg sine theta? Are those all those in the diagram that you're looking at?
I didn't take physics at John Jay, but the way that I was taught to draw them, so the FG equals mg is like summative of mg cos theta.
No, that's right. So that's right. So that's why I'm asking. No, there's many different ways to do it. Totally cool. So what arrow? Yes. So that is right. So what arrows did you put in your?
So in my diagram, so I drew one picture of the scenario where I drew the force of tension and then FG, and then in that same picture, I drew mg cos theta, mg sine theta, and showing that they're summative.
See that? Okay, so maybe this could be very intense on my part or like very picky perhaps, but this is what I think. I totally know people do this all different ways at different colleges and stuff, but because I fully agree that mg, this is a sum of mg cosine and mg sine, like I definitely, like I'll give full credit for a diagram where there's just mg and the tension, or I'll give full credit for a diagram where there's mg sine and mg cosine and the tension. And I'll even give full credit for like two different diagrams, or like in your case, I like the fact that, and I think I remember this, that you made one picture like of the situation and then specifically made the free body diagram. All of that is good, but my one picky problem is if in one single free body diagram, you depict both mg and the mg sine theta, mg cosine theta, that means that we're double counting. That I read that diagram to mean that there's two forces, like you're double counting gravity. Then you're putting in, yeah.
Even if showing
go
summative, like.
Sorry, say again. Even what?
So even if it's, I mean, maybe it's not completely clear that the mg cos theta and mg sine theta are summative to make mg.
But I think but here's the point. The reason that you do that, and I'm totally listening to it. And I know I'm also admitting this is where I am. I don't think I'm wrong, but I certainly know that I'm being at least very, very picky, so I definitely think this is worth the discussion. But here's my thinking on it is, and you're definitely not alone. I know there's other people this happen to too. My thinking is that first in the diagram, we put in the mg because it's there, because we know it's there. But then we can't actually work with it because it's not on the same axis as tension. So the reason we break it up is to get all the forces in one coordinate system. And you can choose whatever coordinate system you want. Like you could technically even just leave mg alone and break up the tension. Like there's different things one could do, but what one's trying to accomplish is ultimately to do the math, make sure that all of the arrows are either parallel or perpendicular to each other. And so so I do agree, like, and I don't think anything it's clear from even talking to you, like I get what you're saying. And so say we were in my office, right? Here's really how I work. If we were like actually in my office right now and I weren't like freaked out about time, even just hearing you, I'm already convinced that yes, you're showing, I get your reasoning. I do get your reasoning, and I certainly don't think you were cheating. Like definitely don't think that. And I don't think that you were writing down something that you had no clue of. I think I'm on a refined level arguing that if you really want to make these free body diagrams do something for you, if we want to make them, then what we want to do is like, to break up the mg into its summative parts so that we can toss it out of the diagram. Like it's actually messing up the diagram until we break it up. So, which is why in general, I would accept one or the other and why I take off the points. But now here, if we were in our office right now, I can tell you right now, say, I believe did I take off 3 points there or 2? I took off 3? Sorry?
It was 3.
3. So I'll say, and whoever's listening right now, this is like not just about Aaliyah, this is about just based on this discussion, both based on the fact that you're taking the time and being polite, and like, I know you care about your points as you should, but I hear that you're also willing to like listen to me about the physics. So just based on that interchange, I'm totally happy to give 2 points back right now. I want to keep one just as the teacher as like a please in the future. Like even if that wasn't an emphasis in other courses, I really think it's a much better thing to do. So I'll keep 1 point to myself as in that jerky authoritarian way. But I'm happy to, even though if we're both understanding each other, like I'll give you back 2 points just because I get the mindset that you're saying.
I think, I completely understand like why because I did draw 2, so I completely understand like the inaccuracies by the first one, but since I did include one that was correct.
That's a good argument. All right, so hold on. So hang on. I hear that. All right, so before you get off the phone, right now, I'm going to fix it so that you should get an email in a second that shows the 2 point. And I'm intentionally saying this to you and to anybody like this because I do hear the only reason I have to be so. You can imagine now, like, of course, if there was infinite time, like everybody would start running.
Yeah,
right. And we just wouldn't have time. But yeah, but hang on. Don't leave until you see that the points have been sent back. Hold on 1 second. But that, not to hold you, but I know if I don't do it right now, I will totally forget. So hold on.
And then also in general, do you prefer if we really like write out every single step of things that we're doing.
Yeah, so on an exam, and I know that makes it difficult in its own way, but yes, if when in doubt, just drag it all out, like basically pretend that I don't, that you're writing it to your dad or like your neighbor down the street, and like the more steps you give me, the safer, definitely all around. Hold on, where'd you go? Okay, because in other words, I'll never take off points for too much, like unless it's literal bullshit. So yeah, that is a safe. Where'd it go? I'm just trying to do this fast so I can get you this thing back. Where is it? Ah, here. Okay. Aaliyah. Am I saying it right? It's Aaliyah, right? Or am I saying it wrong? Is Aaliyah the right way to say it, or is it?
Yeah, that's it.
Okay. All right. So now, okay, here we go. Tell me if you should get an update right now of those 2 points.
Thank you. I appreciate it.
Oh, no, thank you very much. And if you find another, by the way, also, assuming grades are due by, this is also the kind of thing, since if you don't mind going in front of people, if in the middle of the other exam, if you find something from this and you put it in the stream, like I will take it seriously. It's just a matter of time, but this doesn't mean you can't find other things there too. I mean, if that makes sense. Like there's no shutdown until the shutdown. Okay. So wait, so you got that? Anybody else?
Okay, well, thank you.
Thank you very much. Appreciate it. Oh, where do you go to school, by the way? I'm sorry. Where do you go to school? Just curious. Oh, too late. Okay.